Tonight, nearly 20,000 light-years away, hidden behind thick curtains of interstellar dust, a star is burning at a scale that is hard to believe. By one widely repeated estimate, if it traded places with our Sun, its surface would envelop Mercury, Venus, Earth, Mars, and Jupiter, before reaching approximately as far as Saturn's orbit. Its name is Stephenson 218, and it may be the biggest star ever discovered. Maybe because tonight we will find that crowning the largest star is one of the hardest, most carefully argued problems in astronomy. We will climb from our own familiar sun to giants that defy imagination, meet the people who measured them, and learn how much of the answer we can trust. There is nothing to memorize. No test waits at the end. Just a long, gentle journey upward in scale, one step at a time. So dim the lights, get comfortable, let your shoulders drop, and come with me now to meet the largest fires in the night. Every journey needs a first step, and every measurement needs a ruler. So, before we go anywhere near the giants, we begin with the one star you already know better than any other, the one that warmed your face at some point today, whether you noticed or not, the one that was waiting outside your window this morning, the way it has waited outside every window you have ever slept behind, and every window your parents slept behind, further back than anyone kept count. Our sun, it might seem like a strange place to begin a story about the biggest star ever discovered, beside the monsters waiting later in our journey. The sun will look like a grain of sand resting next to a beach ball. But that is why we start here. This is a story about scale. And scale means nothing without something familiar to hold it against. The sun is the standard measuring stick astronomers use when comparing the sizes of stars. They even build the habit into their language. When they describe a giant, they speak in solar radii, which means how many suns, laid side by side, it would take to stretch across it. Every measurement in the hours ahead ultimately belongs to a species that learned astronomy beneath this one star. So let us pick that measuring stick up and feel its true weight before we go anywhere else. You do not need to do anything for this. Just lie back and let the pictures form on their own, the way a room slowly appears out of the dark once your eyes adjust. Start with the light in your room. If any daylight touched you today, even through a curtain, that light made a journey to reach you. The sun sits about 93 million miles away, and according to NASA, its light needs roughly 8 minutes and 20 seconds to cross that gap. Every sunrise you have ever watched was already 8 minutes old when it arrived. Every warm afternoon, every ray that ever fell across a kitchen table, was old news by the time it landed. The sun you see is always the sun of a few minutes ago, a small delay built into every day of your life, so constant that it has never once been interrupted since before there were eyes on Earth to miss it. 93 million miles sounds like a large number, but numbers slide off the mind at night. So let us make it physical. Imagine you could drive there. A comfortable car, a straight highway, 60 miles per hour, no stops. The trip would take more than 170 years. A passenger jet, cruising at 500 miles per hour, would need roughly 21 years of continuous flight, taking off with you as a young adult and landing with you an old one, even the fastest spacecraft humanity has ever flown. The Parker Solar Probe. which NASA has clocked at hundreds of thousands of miles per hour as it swings close to the Sun, still needs weeks to cover distances that sunlight crosses in minutes. That whole gap is what astronomers call one astronomical unit. 1. It is the smallest unit of distance we will use tonight. Everything else grows from here, the way a river grows from a single spring. Now, for the Sun itself. The Sun measures about 865,000 miles across. Our whole planet measures just under 8,000. Line up Earths side by side, like beads on a string, and you would need roughly 109 of them to stretch across the face of the Sun. And if instead of lining them up, you poured Earths inside it, one after another, like marbles into a jar, NASA estimates about 1.3 million would fit before it was full. 1.3 million copies of everything. Every ocean, every mountain range, every city block, every dark bedroom, like the one you are resting in now, multiplied 1.3 million times, and all of it would disappear inside our one ordinary star without leaving a mark. Let that image sit for a moment. There is no rush. The Sun has been this size for a very long time, and it will still be this size tomorrow morning. Here is the first gentle surprise of the night, and it deserves to be told with care, because the easy version is not quite true. You will sometimes hear that our Sun is a below-average star, one of the small, unremarkable ones. The real picture is more interesting. The Sun is a G-type main-sequence star, sometimes called a yellow dwarf. And that word dwarf is the official term. Not an insult, but most stars scattered across our galaxy are red dwarfs. Small, dim, cool stars far lighter than ours. By the numbers. Our Sun is more massive than the majority of its neighbors. A solidly respectable star among the crowd it was born into. So the truth runs in both directions at once. Our Sun is heavier than most stars in the Milky Way. And, beside the giants we are traveling toward tonight, it is modest, almost beyond description. Learning to hold both of those together, without needing one to cancel the other, is the right way to begin this whole climb. The Sun is also, in the most literal sense, middle-aged. Based on the ages of the oldest meteorites in our solar system, scientists estimate it formed about 4.6 billion years ago, and models of stars like ours suggest it has roughly the same amount of time still ahead. It is a star resting in the calm middle of its life, steady, balanced, dependable in a way that almost nothing else in the universe is dependable. That steadiness matters to our story, because the giants ahead, the record holders with the impossible numbers, are anything but steady. Their enormous size is a symptom of something happening to them, something our Sun has not yet begun. Let your body settle a little further into the bed as you hold that thought loosely. It will return before the night is over. Before we leave the Sun, there is one more story hiding inside it, and it may be the most peaceful fact in all of astronomy. Deep in the Sun's core, hydrogen atoms are pressed together so fiercely that they fuse into helium, releasing the energy that eventually becomes sunlight. But that energy does not fly straight out. The way you might picture a lamp switching on, the inside of the Sun is so dense that a particle of light cannot travel more than a tiny distance before it is absorbed and released again in some new, random direction. In, out, sideways, backward, one small stumbling step at a time, like someone crossing a packed room in complete darkness. bumping from shoulder to shoulder without ever finding a straight path. Scientists call it a random walk, and estimates of how long it takes vary depending on the model. But they generally range from thousands of years to well over 100,000 years for energy born in the center of the sun to wander its way out to the surface. Only then does it make that famous 8-minute sprint to your window, which means the warmth that touched your skin today may have begun its journey inside the sun before the first cities were built on Earth. It crossed the interior of our star slower than the whole of human history has unfolded. And then it crossed the emptiness of space in less time than it takes you to fall asleep. Nothing about that process requires anything from you. It happened on its own. The entire time, people were being born and growing old, and forgetting and remembering. And it will keep happening tonight. And every night after, whether or not anyone is awake to think about it. So this is our ruler, held up and felt properly for the first time. A star 109 Earths wide. A star that holds, according to NASA, about 99.8% of all the mass in our solar system. So dominant that every planet, moon, and comet combined adds up to little more than a rounding error beside it. A star so large that no picture book has ever drawn it to true scale next to the Earth, because the Earth would vanish into a dot too small for any printer to reproduce. On the ladder we are about to climb. This is the first rung, the lowest one there is. Take a slow breath here, and let it out a little longer than you took it in. Because now that you can feel the size of one sun in your body, we are ready for the question that started this entire field of study. The question our species needed thousands of years just to think to ask. All those other lights scattered across the night sky. The little silver points you could cover with a fingertip held at arm's length. What if every one of them is another sun? And what if some of them, somewhere out past the edge of what any eye can see, are bigger? That question has an answer, and it is stranger and more moving than anyone who first asked it could have guessed. It begins the way most of the best true stories begin, with a few people looking up at the same tired old sky and slowly, stubbornly, changing their minds about what they were seeing. Go back, for a moment, to the last time you stood outside under a truly dark sky. Maybe it was a camping trip, or a late drive through open country, or one clear evening in a backyard when the porch lights happened to be out. Remember how the stars looked. Small, silver, cold, pinpricks scattered across a black ceiling, so tiny that you could blot out any one of them with a fingertip held at arm's length. Hold that memory. Because here is the astonishing thing about it. For most of human history, nearly everyone who looked up at that sky believed that what they were seeing was, more or less, exactly that. Small lights, perhaps holes in a great dark curtain with fire burning behind it, perhaps lanterns fixed to a distant, turning crystal sphere. The stars were thought to be little because they look little, and for thousands of years there was no obvious reason to believe the sky was lying. The sun sat in a completely different category. The sun was enormous, warm, obviously powerful, close enough to feel on your skin. The idea that the sun and the stars might be the same kind of object would have sounded, to most ancient people, the way it might sound to you if someone said a mountain range and a grain of sand were at bottom the same thing. And yet, scattered across the centuries. A few restless minds wondered anyway. In ancient Greece, a philosopher named Anaxagoras looked at the sun and suggested, out loud, that it was not a god at all, but a huge glowing mass of blazing rock, larger than entire regions of the earth. It was a dangerous thing to say in his time, and it made him deeply unpopular among people who preferred their sky sacred and unexplained. He could not prove it. No one alive then could prove anything about the stars. But the question had been spoken, released into the world like a stone dropped into still water. And questions like that have a habit of waiting, sometimes for centuries, until someone arrives who can answer them. The waiting lasted a very long time. Then, in the late 1500s, an Italian thinker named Giordano Bruno pushed the old question further than almost anyone before him had dared. He proposed that the stars were not lanterns fixed to any sphere. They were suns, other suns, scattered without number through endless space, so far away that their fire had shrunk to a whisper of light by the time it reached us. He even imagined that those distant suns might have their own planets, turning in the dark the way our Earth turns around ours. Bruno was a philosopher, not an astronomer. He had no telescope, no measurements, nothing but reasoning and a stubborn imagination. But it is remarkable, lying here tonight, to realize that a man in the 1500s closed his eyes and pictured something startlingly close to the universe we now know to be real. Proof needed instruments, and the first great instrument arrived in the early 1600s, when Galileo Galilei turned a simple telescope toward the night sky. His little tube of ground glass changed nearly everything it was pointed at. Mountains appeared on the smooth face of the moon. Moons appeared circling Jupiter, where no one had ever seen anything. Countless new stars appeared through the pale band of the Milky Way. Far too many for anyone to have imagined. But when Galileo turned his telescope toward the bright stars themselves, something strange happened. The planets grew larger in his eyepiece the more he magnified them. They swelled into small, round disks, little worlds. You could almost believe you were circling above. The stars did not. No matter how much he magnified them, they refused to become disks. They stayed sharp, brilliant points, unmoved by all his effort. Think about what that small refusal was telling him. If something grows larger as you approach it, it must be somewhere nearby. If it stays a point, no matter how hard you look, it is either impossibly small or almost unthinkably far away. The stars, every one of them, were choosing the second answer. Their stubbornness in Galileo's eyepiece was itself a kind of measurement, the first rough hint that the distances involved were beyond anything humanity had a word for yet. Let your shoulders sink a little heavier into whatever is holding you. None of this needs to be memorized. It only needs to be felt, the way it must have felt to the people living through each piece of it. A few decades after Galileo, the Dutch scientist Christian Huygens tried to put a working number on the idea, using nothing more than sunlight and a clever piece of reasoning. His logic was beautifully simple, if serious. The brightest star in our night sky is truly a sun like ours. Then it must look faint only because it sits so much farther away. So Huygens made a small hole in a screen, let a thin thread of sunlight pass through, and kept shrinking the opening until the sliver of sun looked about as bright to his eye as Sirius looks at night. Then he calculated how far away our sun would have to be moved to appear that dim? The answer was tens of thousands of times the distance between the Earth and the sun. His number, it turned out later, was far too small, because Sirius is in reality considerably brighter than our sun, a fact Huygens had no way of knowing, but the spirit of the experiment was right, and the message underneath was unmistakable. If the stars are suns, then the emptiness around us is deeper than any ocean anyone had tried to imagine. Still, all of this remained educated hope rather than settled knowledge. The final proof arrived in the 1800s, and it came from a direction almost nobody expected. Not from bigger telescopes, from rainbows. In 1814, a German lensmaker named Joseph von Fraunhofer was testing the quality of his own glass, spreading sunlight into its familiar rainbow with a prism, and he noticed something no one before him had properly studied. The rainbow was interrupted. Hundreds of thin, dark lines crossed it, like gaps where certain exact colors had been removed. He mapped every one of those lines without knowing what they were. Then, in 1859, two scientists working together in Germany, Gustav Kirchhoff and Robert Bunsen, uncovered the key. Every chemical element, they found, produces its own pattern of colored lines when heated. A pattern as distinctive as a fingerprint pressed into ink. The dark gaps in sunlight were the fingerprints of elements burning inside the sun itself, each one absorbing its signature colors on the light's way out into space. Feel the size of that discovery. Light, all by itself, carries a list of ingredients folded inside it. For the first time in history, people could learn what a distant fire was made of without touching it, without leaving home, simply by reading its light carefully enough. So scientists turned the new trick on the stars. When they spread starlight into its colors, there were the same lines again, the same fingerprints. Hydrogen in the sun, hydrogen out among the stars. The sky had answered the ancient question at last, and the answer was yes. The stars are suns. Every pinprick you can cover with a fingertip is a furnace, many of them larger and brighter than our own, shrunk to a whisper by distance alone. There is a lovely footnote tucked inside this story. In 1868, astronomers studying the sun's light during an eclipse found a fingerprint that matched no element then known on Earth. They named it helium, after the Greek word for the sun. It was not found on our own planet until 1895, nearly 30 years later. For those 30 years, humanity knew of an ingredient burning in the stars before anyone had held a trace of it in a laboratory jar. We learned something true about the sky before we learned the same thing about the ground beneath our feet. So let the night sky in your memory change shape now, the way it slowly changed for our whole species. Those are not lanterns above your roof. They are suns, thousands visible on any clear night, and hundreds of billions more scattered through our galaxy, each one pouring out light steadily, whether or not anyone is watching. And the moment humanity accepted that, a new question rose up softly behind it. The question that owns the rest of our night. If they are all suns, they cannot all be the same size. Some must be smaller than ours, and some, somewhere out in that deep, unmeasured dark, must be bigger, perhaps enormously bigger, but to know which ones. Wanting an answer is not enough. You have to measure, and measuring a fire you cannot touch. At a distance, light itself needs years to cross, turned out to be one of the most delicate arts our species has ever learned. That art fits neatly into pictures your own body already understands. Before we meet the giants, we need to learn, without any hurry, how anyone could know how big a star truly is. This chapter is the foundation everything else tonight rests on. Every record holder we visit later, every claim about the biggest star ever discovered, depends on the methods you are about to hear, and once you understand them, you will also understand why careful astronomers choose their words so carefully, and why the answer waiting at the top of our climb comes wrapped in an asterisk we will face openly when the moment is right. The good news is that every part of it grows out of something your body already knows how to do. Start with this. If you were sitting upright, you could hold one finger out at arm's length and close only your left eye, then only your right. You do not have to do it. Just remember how the trick looks. The finger seems to jump sideways against the far wall, even though it never moved. Your two eyes see the world from slightly different places, and nearby things shift more than distant things when you switch between them. Your mind uses that tiny shift constantly to judge depth, without you ever noticing the calculation. It is called parallax, and it is the oldest measuring tape in astronomy. Astronomers made the same trick enormously bigger. Instead of two eyes, a few inches apart, they used two positions of the Earth itself. Our planet circles the Sun once a year, so its position in January and its position in July are separated by roughly 186 million miles. Photograph a nearby star from both ends of that colossal baseline, 6 months apart, and the star should appear to shift, ever so slightly, against the more distant stars behind it. Measure that shift precisely, and simple geometry hands you the distance, simple to describe, brutally hard to do. The shifts are so small that for centuries, every attempt to catch one failed. The stars would not budge, which only proved, again and again, how staggeringly far away they were. Generations of astronomers spent careers chasing that little jump and never caught it. It was not until 1838 that a German astronomer named Friedrich Bessel measured the parallax of a star called 61 Cygni. After months of painstaking observation, night after night, the shift he detected was about 1/3 of 1 second of arc, an angle almost too small to be real. To picture it, imagine the width of a single human hair, viewed from well over 200 feet away, roughly the length of 5 school buses, parked bumper to bumper. That was the jump Bessel was hunting. That faint whisper of movement, caught and confirmed, became the first true measurement of the distance to any star, and it placed 61 Cygni about 10 light years from where you are lying right now. A light year, since we will lean on it all night, is the distance light travels in 1 year. Light covers about 186,000 miles every second. In 1 second, it could circle the Earth about 7 times. Let it run for a full year, and it crosses nearly 6 trillion miles. That is 1 light year. The star Bessel measured sits 10 of those away. The giant waiting at the end of tonight's climb sits, by current estimates, nearly 20,000 light years away. Do not try to hold that number. Let it pass over you like weather outside a window. The point of tonight is not to grasp these distances. It is only to float on them for a while. So parallax hands us distance. at least for stars close enough that the trick works. Now comes the second step, and it uses a piece of everyday wisdom you have known since childhood. Lights look dimmer the farther away they sit. A porch light across the street is comfortable to look at. The same bulb a foot from your face would be harsh. Physics makes this relationship precise. Brightness fades with distance in a perfectly predictable way. So, if you know how far away a star sits, and you measure how bright it appears from Earth, you can calculate how much light it truly pours into space. Astronomers call that true output its luminosity. It is the difference between how loud a voice sounds across an open field and how loud it is standing beside the speaker. And here, the fingerprints from our last chapter return with one more gift. The rainbow hidden in a star's light does not only reveal what it is made of, it reveals its temperature. Stars glow in colors that follow their heat, and the scale runs backward from what human habits expect. We say red hot to mean danger, and we picture blue as the color of ice. Among the stars, red belongs to the coolest surfaces, and blue-white to the hottest. You have seen this yourself without naming it, in the low orange glow of dying campfire embers, and in the fierce blue flicker at the base of a candle flame. Read a star's color and its spectral lines carefully enough, and you know the temperature of a surface no thermometer will ever touch. Now watch the last piece fall into place, because this is the sentence the rest of tonight stands on. Temperature tells you how much light each patch of a star's surface gives off. A hotter surface shines more fiercely from every square mile of itself. So if a star glows cool, a deep ember red, and yet pours out tens of thousands of times more total light than our sun, only one explanation is left standing. It must have an enormous surface, thousands upon thousands of dim red acres, each contributing a little, adding up to one overwhelming flood of light. The star must be huge. That is the whole quiet arithmetic behind nearly every giant we will meet. Distance from parallax, true brightness from distance combined with appearance, temperature from color, and from brightness and temperature together, César. No tape measure ever leaves the Earth. The star tells us its own size, using nothing but its own light. If we learn to listen carefully enough, but notice something about that chain of reasoning, because it matters more than anything else in this chapter. Notice what everything hangs from. The first link, distance. If the distance is wrong, everything built on top of it is wrong with it. A star, believed to sit farther away than it truly does, will be credited with more brightness than it has, and therefore with more size. A small error at the first link becomes a large error by the last, and for the most distant giants, parallax shifts become so vanishingly small that even our finest modern instruments, including the European Space Agency's Gaia Observatory, which has measured the positions of more than 1 billion stars, begin to reach the edge of what can be reliably measured at all. That is not a failure of science. That is science showing you, honestly, where its own confidence runs out. Keep that loosely in mind as we climb, because it explains something you will hear echoed all night. It explains why the list of the largest known stars keeps changing over the decades. Why a star can wear the crown for 10 years and then hand it, without drama, to another star. Not because either star changed, but because our measurement of a single distance improved. The stars are not competing with one another. Only our numbers are. There is one more way to measure a star. the most direct of all, and it borders on too bold to believe. Instead of calculating a star's size through its light, you can try to see its true width, catching the tiny disk that Galileo's telescope could never resolve. For a long time, this was considered close to impossible. The stars sit so distant that even a true giant appears smaller in our sky than a coin viewed from hundreds of miles away. And yet, in the early 1920s, on a mountaintop in California, a small group of scientists attempted it anyway, with an instrument of astonishing cleverness, aimed at a red star in the shoulder of Orion. What happened on that mountain gave humanity its first direct look at the true size of another sun. Let your breathing slow a little now, and let the methods fade into the background where they belong. Having done their work, from here on, our journey is made of stars, each one larger than the one before. And the first true giant is waiting in the most famous constellation in the winter sky, Orion. Find Orion somewhere in your memory. Almost everyone across the United States and Europe has seen it at least once. Even people who could not name another constellation. 3 bright stars in a short Tida row, the famous belt, hanging in the winter sky like something placed there by hand. Maybe you learned it as a child, pointed out from a car window on a cold drive home. Maybe someone showed it to you once in a parking lot, breath fogging in the air, and the pattern stayed with you, the way certain small gifts do, long after you forget who gave them to you. Now look up and to the left of that belt, toward the hunter's shoulder. There sits a star that does not look like the others around it, even to the naked eye, even from a bright city sidewalk. It glows with a warm color, somewhere between orange and deep red, like a coal that has refused to go all the way out. Its name is Betelgeuse. Astronomers classify it as a red supergiant, one of the largest kinds of star known, and it happens to be the nearest one of its kind to Earth, which is precisely why it became the first star, other than our Sun, whose width humanity ever directly measured. That measurement happened in December of 1920 on the summit of Mount Wilson in California. And the story that deserves to be told slowly, because it is one of the most beautiful nights in the history of science. At the top of that mountain stood the largest telescope on Earth at the time, the Great Hooker Telescope. Its mirror, a full 100 inches across. But even that machine could not simply photograph the disk of a star. Remember what Galileo discovered 3 centuries earlier. Stars refuse to become disks under magnification. The turbulence of our own atmosphere smears their light into shimmering points. And no telescope of that era could see cleanly through the blur, no matter how large its mirror. So, a physicist named Albert Michelson proposed a way to cheat the problem. Michelson was already famous. He had spent his career measuring light itself with extraordinary precision, and he had become the first American to win a Nobel Prize in the sciences. His idea for Betelgeuse was elegant and strange. Do not try to see the star's disk at all, he suggested. Instead, mount a long steel beam across the top of the telescope with small mirrors near each end, and let the instrument catch 2 separate samples of the star's light, gathered from 2 points spaced far apart along that beam. When the 2 beams are brought back together, they interfere, creating a delicate pattern of fine, alternating stripes. Hidden in the behavior of those stripes lies the answer. If the star were a true point of light, the stripes would stay crisp no matter how far apart the mirrors sat. But if the star has real width, then, as the mirrors slide farther apart, the stripes gradually wash out and vanish. Find the separation where the pattern disappears, and the mathematics hands you the star's angular size. In other words, you measure the width of a distant fire not by looking at it, but by listening to how its own light waves fall out of step with each other. It remains one of the most elegant tricks our species has ever performed. Michelson worked with an astronomer named Francis Pease, and on that cold December night in 1920, the two of them turned the great instrument toward Betelgeuse. Pease adjusted the mirrors by hand, watching the stripes flicker in the eyepiece as the mountain air grew colder, and, at a certain separation, exactly as theory predicted, the stripes faded away. Betelgeuse had a width, a real, measurable width. Caught at last, the first star in history to show anyone its true face. The angle they measured was almost comically small, about 1/20th of 1 second of arc. To picture it, imagine measuring the width of a garden pea from many miles away. That was the sliver of sky Betelgeuse occupied, and it was enough. Combined with the estimated distance to the star at the time, that tiny angle translated into something enormous. The early calculations suggested a diameter of roughly 240 million miles. The astronomers of that era put it in the plainest terms they could find for the newspapers. If you place that star where our sun sits, the entire orbit of the Earth would lie inside it. Everything our planet has ever traveled through, swallowed whole within the body of one star. Modern estimates, which tend to run larger than those first calculations, suggest the star would reach farther still, toward and quite possibly past the orbit of Mars. The measurement made front-page news around the world that winter. It is worth pausing to feel what it must have been like, opening a newspaper in 1920 and learning, for the first time in human history, that individual stars exist large enough to swallow the orbits of planets. The universe grew that week, not in reality, since it had always been this size. It grew in the human mind, which is where all of tonight's journey is really taking place. A century later, what do we know about Betelgeuse? Here our story meets, for the first time, a theme that will follow us all the way to the top of the ladder. Betelgeuse is a perfect first lesson in how slippery these giants are to measure. We know it is a red supergiant in a late stage of its life. We know it is enormous, but its exact size and distance both remain honestly uncertain. And the scientific literature is refreshingly open about that rather than hiding it. Distance estimates have generally ranged from around 400 to more than 600 light-years. And because size depends on distance, published radius estimates have varied as well, with many modern studies placing it somewhere in the neighborhood of 700 to 1,000 times the radius of our Sun. Part of the trouble is wonderfully strange in its own right. Betelgeuse is so puffy and restless that it does not have a crisp edge to measure in the first place. And it changes in brightness, and even in apparent shape, over time. Measuring it has been compared, by more than one frustrated astronomer, to measuring a candle flame flickering in a light breeze. And this star has one more famous story to tell, a recent one that many people listening tonight may remember living through. In late 2019 and early 2020, Betelgeuse dramatically faded. Within months, it lost so much of its usual brilliance that the change was obvious to casual stargazers with no telescope at all. Orion visibly missing part of its familiar glow. Astronomers called it the Great Dimming. And for a while, headlines around the world, Drace asked one breathless question. Was Betelgeuse about to explode? Because that is, eventually, the expected destiny of a red supergiant, a supernova, one of the most powerful events in nature. And Betelgeuse sits close enough that its explosion would briefly shine in our sky with astonishing brightness. The real answer, when it came, was gentler and, in some ways, lovelier than an explosion. Observations from telescopes, including the Hubble Space Telescope and the European Southern Observatory's Very Large Telescope, published by a team led by the astronomer Miguel Montaguez in 2021, indicated that the star had thrown off a huge cloud of hot material from its own surface, which cooled into fine dust and drifted in front of the star like a curtain, dimming its light from our point of view. The star had not been dying any faster than usual. It had exhaled, rather forcefully, and briefly hidden itself behind its own breath. As for the eventual explosion, it is still coming. On that point, the science is confident. But when astronomers say Betelgeuse will explode soon, they mean soon on a cosmic calendar, with most estimates suggesting sometime within the next 100,000 years or so. It could, in principle, be tonight. It is overwhelmingly more likely to be long after every name in this story has been forgotten. Either way, you can rest easily at Betelgeuse's distance. Scientists expect the event would be a spectacular light show in Earth's sky and nothing more. No danger to anyone sleeping beneath it. So here stands our first true giant, measured by starlight and cold steel on a California mountaintop, a star that would swallow the orbit of the Earth, and, by modern estimates, likely more, a star that breathes dust and refuses to hold still for a perfect measurement. And here is the strange truth we carry forward. Betelgeuse, famous, enormous, the first of its kind ever measured, is not even close to the top of the ladder we are climbing tonight. This magnificent monster, swallower of planetary orbits, is only an early rung. But before we climb higher, we should answer a question that may already be forming at the edge of your thoughts. Why are these stars so big in the first place? Why is our steady little sun 109 Earths across, while Betelgeuse sprawls across the width of planetary orbits? What happened to it? The answer is one of the most quietly moving facts in astronomy. These giants are not big because they are strong. They are big because they are running out of time. Understanding that single fact will change how every star for the rest of tonight feels to you. Let your body settle a little deeper into the mattress now, and let a star grow old alongside us. Every star you have ever seen is, at its heart, a balancing act. That single idea is the one this chapter rests on, and it is simple enough to hold with your eyes already closed. Think about what a star is: an almost unimaginably large ball of gas, mostly hydrogen, held together by its own gravity. And gravity has exactly one desire, patient and permanent. It pulls everything inward, always. Without exception, every atom of a star is being tugged toward its center, constantly, without rest. Left alone, gravity would crush any star down to something tiny in almost no time. So why doesn't it? Because of what is happening deep in the core, down in the heart of a star. Crushing pressure and heat force hydrogen atoms to fuse into helium. And every act of fusion releases a small burst of energy. That energy floods outward. And, as it fights its way toward the surface, it pushes back against all the collapsing layers, pressing in from above. Gravity presses inward. The fire pushes outward. And where those two forces meet, they hold each other still. That balance is a star, not an explosion, not a collapse, but a truce between two forces, renewed every second for billions of years. Our sun is resting in the middle of that truce right now, tonight, while you rest too. It is why the sun is so remarkably steady, why it rose this morning the same size it was when the pyramids were built, the same size it was before there were eyes on Earth to see it. As long as hydrogen fuel remains in the core, the balance holds, and astronomers call stars in this long, peaceful phase main sequence stars. It is the calm adulthood of a star's life. And it is where our sun has lived for about 4.6 billion years. But no fuel lasts forever. Over billions of years, the hydrogen in a star's core gets used up, converted into helium ash that settles toward the center. When the core finally runs low on usable hydrogen, the outward push begins to falter. Gravity, which has been waiting the whole time with undisturbed patience, begins to win. The core starts to compress under its own weight. Now comes the twist, the beautiful backward turn that explains every giant in tonight's sky. You might expect a star running low on fuel to fade, shrink, and go dim, the way a campfire dies down into embers. Instead, the opposite happens. As the core compresses, it grows hotter, fiercely hotter, and that surging heat ignites fusion in a fresh shell of hydrogen surrounding the core. Fuel that had never before been hot enough to burn. This new shell of fire burns more furiously than the old core ever did, and it pours out so much energy that the star's entire outer envelope gets pushed outward, and outward again, swelling to tens or even hundreds of times its former size. The star inflates, slowly, like a great balloon left near a low flame, and as its surface spreads across that enormous new area, the surface cools, and its color slides from white or pale yellow down toward orange and finally deep red. Remember the backward temperature scale from earlier tonight. Red is the color of the coolest stellar surfaces, so the star ends up enormous, brilliant, and unmistakably red, all at once. A red giant. Or, if the star was born massive enough, a red supergiant, exactly like Betelgeuse. Let that idea turn over once in your mind, because it carries something profound about everything ahead of us. The enormous size of these stars is not a sign of strength or health. It is a symptom. It is what a star looks like during its final act, burning through its last reserves, swollen and unsteady, in a way it never was, in its long, quiet youth. Nearly every star competing for the radius record is in a late and unstable stage of stellar evolution. In astronomy, the biggest things in the sky are the ones closest to their own end. There is something almost tender in that fact, and it will color everything for the rest of the night. And this is not only a story about distant monsters, it is also, gently, a preview of home. According to NASA, in roughly 5 billion years, our own Sun will exhaust the hydrogen in its core and begin this same transformation. It will swell into a red giant, growing so large that it is expected to engulf Mercury first, and then Venus. Whether it will reach far enough to swallow the Earth is a genuine question scientists still debate. Some models suggest our planet will be consumed along with the inner worlds. Others suggest Earth may escape outward into a wider orbit as the Sun sheds mass during the process. Either way, long before then, the swelling Sun will have made our world unrecognizable. That can sound like a frightening bedtime fact. So, let me place it in its true proportion. 5 billion years is not a deadline in any human sense. It is longer than the entire history of complex life on this planet. It is a length of time in which everything you have ever worried about could happen, be forgotten, and happen again, millions of times over, with room to spare. The Sun's old age belongs to a future so remote that tonight it can only be a story. And stories like this one are safe to fall asleep to. There is one more piece of this transformation worth carrying with us. Because it explains something strange, we will keep noticing about every giant ahead. When a star swells to hundreds of times its original size, its matter gets stretched astonishingly thin. The star's total mass barely changes, but its volume becomes millions of times larger, so its outer layers become almost impossibly sparse. Out in the swollen envelope of a red supergiant like Betelgeuse, the gas is far thinner than the air you are breathing right now, closer to what an engineer on Earth would call a laboratory vacuum. The deep interior is another matter, dense and furious and crushing, but the enormous outer body, the very part that makes these stars so wide, is barely there in any physical sense. Some astronomers have described these swollen stars, half-jokingly, as red-hot vacuums, vast glowing envelopes, thinner than a breath, wrapped around one small, hidden, furious furnace. That thinness is also why these stars are so difficult to measure, and why their published sizes come with honest margins of uncertainty. A star like our Sun has a fairly crisp, visible surface. A red supergiant simply fades outward, with no clean edge anywhere, like fog that never quite decides where it ends. When astronomers disagree about the radius of some giant, this thinning is very often the reason. They are not being careless. They are trying to draw a single, firm line inside a cloud. Pause here for one easy breath, and let all of that settle on its own. So now you hold the secret of the giants. They are old stars in their final chapters, inflated by shells of borrowed fire, thin as mist at their edges, cool and deep red at their surfaces, and enormous beyond anything their younger selves suggested. The bigger the star we meet from here on, the deeper into its own ending it has travelled. With that understanding in place, we can return to the ladder and keep climbing. Because between the shoulder of Orion and the record holders waiting at the top, there are giants that humanity has known and loved for centuries. Stars whose rich colours were admired through old brass telescopes long before anyone understood what those colours meant. One of them glows so richly red that the astronomer who first studied it closely compared it to a garnet, a deep, precious gemstone burning in the northern sky. Another blazes at the heart of the Scorpion, a star so imposing in the ancient world that its name literally means rival of Mars. Those two old friends are waiting just ahead, Before any telescope could measure a single star, people were already collecting red stars, the way some people collect beautiful stones off a beach. Among the thousands of white and pale blue points scattered across a clear night, a truly red star stands out immediately, like one drop of color spilled across an old black and white photograph. In this chapter, we visit two of the loveliest such stars, admired for their beauty for generations, before anyone understood what that beauty meant. Now, thanks to our last chapter, you and I already know their secret. That deep color is the visible glow of old age. We are about to visit two magnificent stars resting in the final chapters of their long lives. The first lives in the northern sky, inside the constellation Cepheus, named for a mythological king, and the man who first fell in love with it was one of the greatest stargazers who ever lived, an astronomer named William Herschel. The same Herschel who discovered the planet Uranus in 1781 and taught humanity that its map of the solar system was still unfinished. Herschel spent countless nights sweeping the sky with handmade telescopes he had built himself, cataloguing nearly everything he found. And he had a habit of writing down not just positions and brightnesses, but personal impressions, the way a traveler keeps a journal on a long trip. When his telescope crossed a certain star in Cepheus one night, he paused. The color stopped him cold. He described it in his notes as a very fine, deep garnet color, comparing its rich red to the gemstone. And he noted how strikingly it stood out beside the pale stars around it. The description stuck, and to this day, more than 2 centuries later, astronomers and backyard stargazers alike still call Mu Cephei by its affectionate nickname, the Garnet Star. If you ever get the chance, on some clear autumn night in the northern hemisphere, to see Mu Cephei through even a small backyard telescope, it is worth the trouble. Observers often describe it as one of the most beautiful sights available to any amateur instrument. A glowing ember set among scattered diamonds. And, for a long time after Herschel, that was all anyone knew about it. A pretty red star, a jewel for collectors of the sky. Then the 20th century arrived with its new toolkit, the fingerprints of light, the arithmetic of brightness and temperature. And the Garnet Star turned out to be one of the largest stars visible to the naked eye anywhere on Earth. It is a red supergiant, like Betelgeuse, but by most published estimates, even bigger. Studies of Mu Cephei have generally placed its radius somewhere around 1,000 times that of our Sun, with some estimates ranging higher. Though, as always with these giants, the figure depends heavily on its distance, which remains uncertain. If a star of that size replaced our Sun, its surface would reach past the orbit of Mars and deep into the asteroid belt, possibly approaching the realm of Jupiter. The little garnet Herschel admired through his handmade eyepiece would swallow every place a human footprint or a human machine has ever touched, with room to spare. There is something moving about the gap between what Herschel saw that night and what the star truly is. He looked directly at one of the largest single objects in our region of the galaxy, and all he could honestly report was a fine, deep color. He was not wrong. He was early. Science often works like that. A long relay in which each generation describes as much as its instruments allow, and trusts some future generation to finish the sentence. Take a slow breath here, and travel south with me, out of the old King's constellation, down toward the warm summer sky, where our second old friend burns at the heart of the Scorpion If the Garnet star is a hidden jewel, this second star is a celebrity. It is one of the brightest stars in the night sky, and nearly impossible to mistake. A brilliant point with a warm reddish glow, sitting exactly where the heart of the constellation Scorpius should be. Cultures around the world told stories about it for thousands of years before anyone had a telescope, and the ancient Greeks gave it the name it still carries. A name that is really a small joke about the sky. They called it Antares, often translated as rival of Ares, or in Roman terms, rival of Mars. Whenever the red planet wanders through that part of the sky, the two red lights sit near each other like competitors sizing one another up, and skywatchers have been comparing their color and brightness ever since. It is a wonderful irony. Knowing what we now know, Mars is a small, rocky world, about half the width of Earth. Antares is a red supergiant sitting hundreds of light years away. Published estimates, including work based on observations by the European Southern Observatory, have placed its radius at roughly 700 times that of our Sun, large enough that its surface would reach out past the orbit of Mars itself. The so-called rival of Mars could swallow Mars whole, along with everything between it and the Sun, and barely notice the meal. The two rivals were never in the same weight class. They were never even in the same kind of existence. Distance alone made them look like fair equals. The same old trick of distance that once made all the stars look like lanterns. Antares has given modern astronomers one more gift, because it is relatively close and enormously large at the same time. It is one of the very few stars whose surface we have begun to see in real detail. In 2017, a team using the European Southern Observatory's instruments high in the mountains of Chile published the most detailed image ever made of the surface and atmosphere of any star other than our Sun. And the star they chose was Antares. What they found was not a smooth, calm ball. It was a churning, uneven surface, with enormous slow currents of gas rising and falling across it. A star simmering in slow motion, like Betelgeuse with its curtain of dust, like every giant ahead of us tonight. Antares is restless. Old stars do not sit still. They churn and shudder and gradually shed themselves into the surrounding space. Both of these stars, the Garnet and the Scorpion's heart, appear headed toward the same kind of ending. Each is generally expected, according to the standard models of how massive stars evolve, to eventually collapse and explode as a supernova, on timescales that sound urgent in astronomical terms and are utterly unhurried in human ones. Nothing in the sky above your roof tonight requires your concern. The Garnet star will still be a garnet tomorrow evening, and Antares will still be outshining its little red rival next summer, and for countless summers after that. Here is where we stand on our ladder now, so you can feel the shape of the climb without holding any single number too tightly. Our Sun, the measuring stick, one solar radius, by definition, Betelgeuse, the first giant with a face, several hundred suns across, by most reasonable estimates. Antares, sitting comfortably in that same magnificent class, and Majoris, the Garnet star, around 1,000 suns across, one of the largest stars the unaided eye can find from Earth. 1,000 suns already, and our ladder is barely half climbed, because sometime in the 20th century, astronomers paying attention to the far southern sky, began studying a strange, unruly star in the constellation of the Great Dog, a star that seemed to be tearing itself apart in slow motion, throwing off arcs and clouds of glowing material like something caught mid-explosion, frozen in the act. When its size was finally estimated, the numbers were so large that some astronomers openly doubted they could be real, and a genuine scientific argument broke out over whether a star that enormous could physically exist. That beautiful, chaotic monster is next, low in the winter sky, trailing behind Orion the whole way. Low in the winter sky, trailing behind Orion like a loyal companion who never quite catches up, there is a constellation called Canis Major, the Great Dog. You have almost certainly seen its brightest jewel, Sirius, the dog star, the brightest star in Earth's night sky, the same star whose light Christian Huygens once tried to weigh against a sliver of sunlight. Centuries ago, but tonight we pass Sirius with only a polite nod, because, a few degrees away, far too faint for the naked eye, sits a star of an entirely different order, a star that, for a long stretch of the 21st century, was widely described as the largest known star in existence. Its name is not poetic. It is a plain catalogue label, V.E. Canis Majoris, usually shortened to VY. And the story of how humanity came to understand what it was looking at is one of the finest examples our journey has to offer of science openly changing its own mind. The star has been sitting in our records for a very long time. It appears in observations reaching back to the early 1800s, when the French astronomer Joseph Jerome Lalande first catalogued it, and for generations it remained one entry among hundreds of thousands. A faint reddish star tucked into the Great Dog. Some 19th century observers noted that it seemed to change in brightness, and some reported it looked faintly fuzzy around the edges. But the instruments of that age could say no more. The first real surprise arrived once telescopes grew strong enough to look closely. VY Canis Majoris is not sitting alone in space. It is wrapped in an enormous, glowing, lopsided cloud of its own making. Arcs and knots and long streamers of gas and dust flung outward over centuries. Detailed studies with the Hubble Space Telescope, led by the astronomer Roberta Humphreys of the University of Minnesota, mapped that cloud and found evidence of a series of massive eruptions, separate outbursts that had each hurled huge quantities of the star's outer layers into space, at different times, in different directions. Like a slow-motion argument the star was having with itself. Humphreys and her colleagues have compared the behavior to gigantic versions of the arcs and eruptions we see on our own sun, scaled up to a degree that is hard to hold in the mind. On the sun, such an eruption is a ribbon of glowing gas. On V, single eruptions appear to have carried something on the order of the mass of Jupiter, or more, away from the star in one convulsion. So this is not a star with ordinary weather. This is a star coming apart at the seams, slowly, episodically, shedding itself into the dark like a mountain wearing down under repeated storms. Except the storms come from inside. Astronomers classify VY as a red hypergiant, a category even rarer and more extreme than the supergiants we have met so far, reserved for enormous stars caught in an especially unstable, especially brief phase near the end of their evolution. Only a small handful of stars like it are known in our entire galaxy. In meeting VY, we are meeting something the galaxy almost never lets anyone catch in the act. Now for the argument. Because in the early 2000s, VY Canis Majoris started a real scientific fight. When astronomers combined estimates of the star's distance, brightness, and temperature, the same arithmetic we learned earlier tonight, some calculations produced a radius of 1800 solar radii, and, by certain estimates, considerably more, with figures approaching 2,000 suns or beyond appearing in the published literature, numbers that large collided head-on with theory. Models of how stars work suggested a star could only grow so large before its outer layers became too loosely bound to remain attached at all. By the most generous estimates, seemed to be flirting with that limit, or sitting past it. And so, through the 2000s, careful papers were published that openly disagreed with one another. One camp argued VY truly was among the largest stars physically possible. Another camp argued the measurements were being fooled, that the star's dusty cocoon was confusing the numbers, and that VY was in reality far smaller, perhaps only around 600 solar radii. Still a colossal giant, but no record holder. Notice how calm the resolution of that fight was, because it carries the spirit this whole journey is built on. Nobody settled the disagreement by arguing louder. They settled it by measuring better. Improved observations through the 2000s and into the 2010s, including interferometry, the same family of technique Michelson pioneered on Betelgeuse a century earlier, along with better distance measurements drawn from radio observations of the star's surroundings, gradually narrowed the range. Much of the modern literature has converged on estimates in the region of roughly 1400 solar radii, with honest uncertainty attached, placing VY firmly among the largest stars known, though very likely not the single largest. The wildest early numbers softened. The doubters' smallest numbers grew. The truth turned out to live between the two loudest claims. And it took nearly 20 years of patient, unglamorous work to find it. Let your jaw and your hands soften for a moment, and let us feel the size that remains. Because even the cautious number is barely believable. 1,400 suns across. Placed at the center of our solar system, VY's surface would reach well beyond the orbit of Jupiter. Sunlight crosses the width of our own sun in about 4.5 seconds. A single blink. To cross the face of VY Canis Majoris, light would need around 2 hours. To travel all the way around it, tracing its full circumference, light would need roughly 6 hours. A beam capable of circling the entire Earth 7 times in 1 second would spend most of a working day making 1 lap of this star. And if you attempted that lap in a passenger jet, flying day and night at 500 miles per hour, the journey would take something like 9 centuries. A crew that lifted off in the age of castles and crusades would only now be touching back down, and all of that immensity is dissolving. That is the strange tenderness of VY Canis Majoris. By the estimates published in studies of its outflows, the star has already thrown off a substantial fraction of itself, and it continues losing mass at one of the highest rates known for any star. Like its smaller cousins tonight, it is generally expected to end in a supernova on a time scale of perhaps 100,000 years or so. Though with a star this unstable, the honest answer is that nobody can say precisely when. What we can say with confidence is what we see, a star so large that light needs hours to circle it, standing in the wreckage of its own eruptions, glowing deep red through a haze of its own making, finishing the last chapter of a story that began millions of years before there were human eyes to read it. For a long stretch of years, in books and documentaries and classrooms, Canis Majoris wore the crown, the biggest star known to science. Many people listening tonight may have first learned its name that way, with total confidence, from a teacher or a book that had no reason to doubt it. But measurements moved, the way honest measurements eventually do. And the title moved with them. It passed to another star, one that became, for a while, the most famous giant on the internet. A star whose name millions of curious people typed into search engines. A star crowned not by professional astronomers this time, but by ordinary curiosity itself. That star is called Scuti, and its story, the sudden rise and the slow unraveling of an accidental legend, is where we drift next. Every age crowns its champions in its own way. Betelgeuse was crowned by newspapers. In the winter of 1920, in bold headlines set in ink, Canis Majoris was crowned by textbooks and documentaries, decade after decade. But the next giant on our ladder was crowned by something newer and faster than either. It was crowned by the internet. And to understand how a faint star in a small, obscure constellation became, for the better part of a decade, one of the most famous objects in the night sky, we start where its story begins. In the summer of 1860, at an observatory in Bonn, Germany, the astronomers working there were engaged in one of the most patient, unglamorous projects of the 19th century, a great survey of the sky, methodically cataloguing star after star, hundreds of thousands in total, position by position, night after night. Somewhere deep inside that ocean of bookkeeping, they recorded a faint reddish star in the constellation Scutum, the shield. Nothing about it seemed remarkable. It was one entry among 1/3 of a million. But when observers checked it again years later, they found it had changed its brightness. The star was a variable, slowly pulsing, brightening and dimming over a cycle stretching across hundreds of days. Under the naming system used for such stars, it received the plain designation it still carries, Scuti. For more than a century after that, this remained the entire story, a faint, pulsing red star tucked into the shield. The constellation itself is a modest one, easy to overlook on a star chart, sitting inside a rich, crowded band of the Milky Way, and it carries a gentle piece of history worth pausing over. Scutum is one of the very few constellations ever named to honor a real historical event, created by the astronomer Johannes Hevelius in the 1680s to commemorate a Polish king's shield. So this small patch of sky is itself a kind of quiet memorial, a small room tucked inside the sky's much larger house. And inside that room, unnoticed, one of the largest stars ever seriously studied sat pulsing softly for 150 years. The transformation arrived in the early 2010s. A team of astronomers, led by Benjamin Arroyo Torres, working with the Very Large Telescope operated by the European Southern Observatory in the mountains of Chile, turned interferometry directly on Scuti. With the key observations taken in 2012 and the results published the following year, this was the same family of technique Michelson and Pease pioneered on Betelgeuse, refined by 90 additional years of engineering. They measured the star's tiny, angular size directly. Then they combined that measurement with the best available distance estimate at the time, roughly 9,500 light-years. The arithmetic produced a radius of about 1,700 solar radii, 1,700 suns across. At the time, that number placed Scuti comfortably above every other reliably measured competitor, above Betelgeuse, above the Garnet star, above the settled estimates for Canis Majoris, and so, quietly at first, encyclopedia entries began to change. Reference lists were edited. Then the internet did what the internet does best. Videos comparing the sizes of stars were becoming enormously popular in those years, racking up tens of millions of views apiece. The camera pulling back from Earth, to the Sun, to giant after giant, each one dwarfing the one before, and at the end of nearly every one of those videos, waiting like a final chord, sat Scuti, the biggest star known to humanity. Its name was typed into search engines by millions of people. Children learned it in school. For a solid decade, if you had asked almost anyone who cared about space to name the largest star, the answer came back, Scuti, delivered with the easy confidence of settled fact. But you have been climbing with me long enough to hear the question hiding under all that confidence. The measurement of 1,700 suns stood on two legs. The angular size, which had been measured beautifully, and the distance, which was never measured directly at all, only estimated. Remember the chain we built earlier tonight. If the distance is wrong, everything built on top of it is wrong with it. In 2018, a new kind of evidence arrived, and the famous number began to wobble. The evidence came from Gaia, a space observatory launched by the European Space Agency in 2013, and Gaia deserves a moment of appreciation, because it is one of the most quietly heroic machines our species has built. Gaia's entire purpose is parallax, the same ancient finger trick from our earlier chapters. The tiny shift of nearby stars against the distant background, performed now with a precision Friedrich Bessel could never have dreamed of. Sitting in space, free of our blurry atmosphere, Gaia has measured the positions, motion, and distances of well over 1 billion stars, refining those numbers with each new release of its data. When Gaia's second major data release arrived in 2018, it included a fresh parallax measurement for Scuti, and that measurement pointed toward a star dramatically closer than the 9,500 light-years everyone had assumed, perhaps closer to 5,000 light-years. Follow the chain. If the star sits closer than assumed, its true brightness must be lower than believed. If its brightness is lower, its calculated size shrinks with it. Analyses built on the new distance suggested Scuti's radius might be closer to about 750 solar radii, not 1,700, roughly the same size class as Antares. But here the story asks for real care, because the tidy version, where Gaia arrived and finally measured everything properly and the old number died on the spot, is too neat to be true. Astronomers who specialize in these stars caution that Gaia's parallax measurements are themselves difficult for red supergiants. These stars are so enormous, and their surfaces churn so restlessly with vast, slow convection currents, that the star's apparent center of light wanders, and that wandering can be a meaningful fraction of the already tiny parallax angle being measured. Imagine trying to pin down the exact position of a candle flame that keeps flickering. The Gaia measurement was serious evidence, not a final verdict. Later analyses, drawing on Gaia's improved third data release, have suggested distances closer to 6,000 light-years, with size estimates in some careful compilations landing near 900 solar radii. So the honest summary is a range, not a single tidy number. Scuti is an enormous star, most likely somewhere in the class of 750 to 900 suns across, whose exact rank remains unknown, and the once famous figure of 1700, repeated across a decade of videos and articles, rests on a distance that current measurements no longer support with confidence. I find something comforting in this story, and I want to offer it to you before we move on. Nothing happened to the star itself. Through the entire rise and fall of its accidental fame, through every list and every video and every one of those millions of searches, Scuti did not change in the slightest. It kept pulsing in its small room inside the shield, exactly as it had since long before Bon, long before Hevelius, long before there was anyone around to catalogue anything. The only thing that rose and fell was a number written in human documents. The universe was never wrong about Scuti. Only our paperwork was. And science, almost alone among human institutions, is built to correct its own paperwork in public, without shame. The famous number wobbling was not an embarrassment. It was the system working as designed. Let one slow breath out here, and let the question follow it naturally. If the title slipped away from Scuti, where did it go? It went to a star that almost nobody outside professional astronomy had heard of. A star with no ancient name, no mythology, no place in any old constellation story. A star so obscure that its popular name today comes from the catalogue of the man who first found its neighbourhood. A careful, thoroughly modest astronomer working through old survey plates, looking for something else at the time. To meet the current candidate for the crown, we first need to meet him, and the quiet, almost accidental discovery he made in 1990. The final approach begins now, and it begins, of all unlikely places, in Ohio. Every star we have met so far tonight carried a story inside its name. Betelgeuse, from an old Arabic phrase describing its place on the hunter's shoulder. Antares, the rival of Mars, an ancient Greek joke about the sky. Mu Cephei, the Garnet star, named for a colour that stopped William Herschel's eye. Names full of history, full of human affection, full of thousands of years of people looking up. The star at the top of our ladder has none of that. Its popular name is Stephenson 2-18. And before we stand in front of the star itself, I want to spend a little time on where that plain name came from, because hiding inside it is one of the gentlest stories of the whole night. A story about the kind of scientist who never becomes famous, doing the kind of work that never makes headlines, and stumbling, in the middle of that work, onto something extraordinary without ever fully realizing it. The name belongs to an American astronomer named Charles Bruce Stephenson. He spent the heart of his career at the Warner and Swazi Observatory of Case Western Reserve University in Ohio, and if you looked up the story of his life, you would find no dramatic turning points, no famous feuds, no legendary night at a telescope. What you would find is catalogues. Stephenson was a cataloguer, one of astronomy's librarians. His specialty was searching through survey images of the sky for certain kinds of unusual stars, then publishing careful, methodical lists of what he found, so that other astronomers, with other instruments and other questions, could follow up later. It is the least glamorous work in science, and it is also the foundation everything else stands on. Every giant we have met tonight sat in someone's catalogue long before anyone understood what it was. Someone has to write the library's index first. Stephenson wrote indexes for a living, year after year. In 1990, he published one such search. He had been hunting through old survey plates for a particular kind of cool, red star, and somewhere in that hunt, he noticed something unusual in the constellation Scuti. Yes, the shield again, the same modest constellation where Scuti pulses. Along that line of sight, the shield looks straight down one of the richest, most densely crowded corridors of our galaxy, toward a region thick with stars and dust alike, and there, buried in that crowded field, Stephenson noticed a tight little knot of faint red stars, clustered in a way that suggested they were not a coincidence of perspective, but a family, a group of stars born together. He included it in his paper as a newly identified star cluster, the second cluster listed in that work, and so it entered the scientific literature under the plainest label imaginable. Stephenson, too. Then, for years, almost nothing happened. The cluster sat in the catalogue the way Scuti once sat in the Bond survey, the way Canis Majoris once sat in Lalande's records, the way so many discoveries sit for a while, filed away. Stephenson himself passed away in the early 2000s, and there is no real evidence he ever knew what his modest cluster 2 would come to mean. He handed the baton forward without learning where the race would lead. By this point in our journey, that pattern should feel familiar. It is the same relay we have watched all evening, each runner carrying the question as far as their instruments allow, then passing it on. The real follow-up arrived in the 2000s, and it needed a technology Stephenson's generation was only beginning to use well. Infrared light. Here is why that matters. In a single, clear image, the region of Scutum, where the cluster sits, is heavily veiled by interstellar dust, enormous cold clouds drifting between the stars. And dust does to visible light what fog does to headlights on a dark road. 2. Looking toward Stephenson, 2 in ordinary light is like studying a distant campfire through miles of smoke. But infrared light, the same kind of light your skin feels, as warmth radiating from a stove, slips through that dust far more easily. When astronomers examined the cluster with modern infrared instruments, the smoke cleared. What emerged from behind the veil was astonishing. In 2007, a team led by the astronomer Ben Davies, working with colleagues including Don Feiger and Rolf Kudrycki, published a detailed study of the cluster, and it turned out that this faint knot of stars was one of the most remarkable stellar families known in our galaxy. Stephenson 2 contains By that study's count, roughly 24 red supergiants, all apparently born together, all now growing old together in the same small neighborhood. Let that register for a moment. Red supergiants are rare. They represent the brief final act of only the most massive stars. A phase so short in cosmic terms that catching even one is considered fortunate. Betelgeuse is essentially the only one most people can point to in the sky. And here, packed into a single cluster behind the dust of the shield, sat around 20 of them at once. One of the largest such gatherings ever identified. Astronomers estimate the cluster lies very roughly 19 or 20,000 light-years from Earth, though that distance, as you will hear again soon, carries honest uncertainty that matters a great deal to everything built on top of it. Rest your eyes on that place for a moment. As a bedtime picture, rather than a fact, a single neighborhood of space where dying giants stand together like ancient redwoods gathered in one grove, each one's Volon, deep red, restless, shedding itself into the surrounding dark, each one destined, in its own time, for the same kind of ending. A whole family of endings, gathered in one small room of the galaxy, hidden behind smoke, waiting most of a century between the night Stephenson jotted it into his catalogue and the nights when telescopes finally saw it clearly. And among all those giants, one star stood out. Here the story needs a moment of extra care, because the popular version smooths over a detail worth keeping. The star we are approaching carries several names, because it appears in several catalogues, each with its own numbering system. In one older numbering tied to Stephenson's original cluster listing, it is recorded as star 18, which is where the familiar name Stephenson 218 comes from. In the separate system used by Davies, Fiege, and Kudrytski in their 2007 study, the same star is designated DFK1, drawn from the initials of their three names, or simply D1, likely because it stood out as the most luminous member of their list. Though the precise logic behind that early numbering is not something later writers have always agreed on. Astronomers today often refer to it more formally as Stephenson 2, DFK1. None of these names was bestowed like a title. They are shelf labels, written by different librarians at different times, all pointing to the same remarkable book. The internet settled on Stephenson 218, and we will use that name too. But it is worth knowing that behind the tidy name lies the ordinary, slightly tangled bookkeeping of real, working science, whatever you call it. When astronomers measured this star's light carefully, something did not fit. It was too bright, too red, too extreme in every measurable way. It outshone its 24 giant siblings so dramatically that researchers began to question whether it could truly be a member of the family at all, or whether the arithmetic behind its claimed size could be trusted. Because, if the raw numbers were taken at face value, this one veiled star in the shield was larger than anything else on the entire list. Larger than Betelgeuse, larger than the Garnet star, larger than VY, Canis Majoris at its most generous published estimate, larger even than UY Scuti's legend at the peak of its internet fame. By one widely cited calculation, this was, almost accidentally, the biggest star ever found, so the climb arrives at its summit. Every rung of the ladder is behind us. Every method, every honest mistake, every correction, every patient cataloguer and careful measurer has carried us here, nearly 20,000 light-years from your bedroom, to the edge of a veiled cluster tucked into the shield, where a star wearing a borrowed name burns at a scale that stretches belief. In the next chapter, we stand before Stephenson 218 itself, and I will show you, plainly, what the famous measurement says, where it comes from, and how it was built piece by piece. Take one long, easy breath and let it go completely. The summit is close, and there is no hurry left in any of it. Here we are, nearly 20,000 light-years from the room you are resting in, on the far side of dust, so thick that the star sits beyond the reach of any unaided human eye. At the summit of the ladder we have been climbing all evening. Stephenson 218. The star that may be the biggest one ever found, and because you have climbed the whole distance honestly with me, you have earned something most tellings of this story never offer. You get to see where the famous answer comes from, piece by piece. So before we let ourselves feel the size, let us watch the number being built, the same way the astronomers built it. Recall the arithmetic from earlier tonight. To size a star you can never visit, you need three things: its distance, its true brightness, and its temperature. Stephenson 218 has never shown anyone its edge directly. It sits too far away, and too deeply veiled, for even our finest instruments to trace its outline. Its celebrated size is not a photograph. It is a calculation, assembled from 3 ingredients, and each ingredient has a story worth knowing. The first ingredient is distance, and honestly, it was borrowed rather than measured. The star sits beside the Stephenson 2 cluster, that grove of 24 dying giants we just met, and the cluster's distance has been estimated at very roughly 19 or 20,000 light-years, using several different methods. If this star truly belongs to the family, it shares the family's distance. That is a reasonable working assumption, not a settled fact, and we will stress test it in the next chapter. The second ingredient is brightness, a frequently repeated reconstruction, drawing on work by researchers, including the astronomer Roberta Humphreys of the University of Minnesota and colleagues studying this cluster, combines modeling of how much energy pours out of the star across the infrared, where its dust-shrouded light reaches us, with an estimate of how much light was lost along the way through the intervening dust. The luminosity that commonly emerges is enormous, on the order of 437,000 times the output of our Sun, nearly 500,000 suns of light, streaming from one object. The third ingredient is temperature. The star's deep red color, along with what can be read from its spectrum, suggests a surface of roughly 3,200 kelvins, which works out to about 5,300 degrees Fahrenheit. That sounds fierce, and it is, but it is still only around half the surface temperature of our Sun. As stars go, this is a cool star. Now for the finishing move, the same one we used on every giant before this one. A surface that glows only softly from each square mile of itself. For such a surface to pour out 400,000 suns worth of light, it must be almost unimaginably vast in area. Run the numbers, and out comes the figure everyone repeats. A radius of approximately 2,150 times that of our Sun. I want to be plain with you about what that figure is, because this is the heart of our whole evening. It is a reconstruction, built from an assumed distance, a modeled brightness, and a somewhat uncertain temperature, combined through a straightforward physical formula. It is not a direct measurement of the star's edge, and the researchers who work on stars like this present it with that kind of caution, not as a finished verdict. What can fairly be said is this: it is one of the largest radius estimates ever seriously discussed in the published astronomical literature. And that alone is why this obscure, veiled object became the destination of our journey. Whether the true size matches the famous number is a question we will hold up to the light in the next chapter. For now, let us do what human minds do best, and feel what 2,150 suns would mean. Begin with light itself, the fastest thing there is. Light crosses the width of our sun in about 4.5 seconds. A single blink. It crosses the face of VY Canis Majoris in around 2 hours. To travel all the way around Stephenson 218, tracing its full circumference at 186,000 miles every second. Light would need close to 9 hours. Think about what that means in the units of a human life. If a beam of light left on that journey the moment you closed your eyes tonight, it would still be circling the star when you woke tomorrow morning. An entire night of human sleep, from your last drifting thought to your first stretch of the morning, fits inside a single lap of one star. Now trade the light beam for something human, a passenger jet, cruising at 500 miles per hour, the pace of every long flight you have ever taken. Flying around the Earth at that speed takes about 2 days. Flying around our sun would take roughly 7 months. Flying once around Stephenson 218, day and night without landing, would take on the order of 1,300 years. A crew that lifted off while the Vikings were still sailing would only now be touching back down, having done nothing else the entire time but circle one star. And the volume? This is the number I suggest you do not try to hold, but let pass over you like weather outside a window. If the famous radius is accurate, you could fit something on the order of 10 billion of our suns inside Stephenson 218. 10 billion suns, poured into one. And remember from the beginning of tonight that each of those suns could hold about 1.3 million Earths. The multiplication produces a figure with no place left in ordinary imagination. And it does not need one. It asks nothing of you. Under that same estimate, if the star traded places with our sun, its surface would reach out roughly 10 astronomical units, which sits right around the average orbital distance of Saturn, and possibly a touch beyond it, depending on where Saturn happens to be along its slightly oval path. We will take that walk properly, planet by planet, a little later tonight. For now, hold the outline loosely. Everything from Mercury out through Jupiter, gone inside. Saturn itself grazing the edge of the fire. What is this giant like? Then, as a presence rather than a collection of numbers, the measurements sketch a portrait we can trust in its broad strokes. Even while the exact size stays open, it is deeply red, cool at the surface, by stellar standards, ferociously luminous in total, and restless. Observations indicate it is steadily shedding mass into the space around it, wrapped in its own gradual exhalation of gas and dust, like every other red giant we have met tonight, only at perhaps the grandest scale yet known. It is doing what all of them are doing, burning its final reserves, swelling, loosening its grip on itself. This star is not a triumphant object at the top of a list. It is a star deep in its last act. And its size, whatever the final measurement turns out to be, is the shape of its own ending. One more image before we face the asterisk, and it may be the gentlest one of the night. For all its staggering scale, Stephenson 218 appears in our sky as nearly nothing. Veiled behind 20,000 light-years of dust, it sits far too faint and obscured to be seen with the unaided eye. Detectable chiefly through specialized infrared surveys rather than ordinary starlight. A shelf label tucked into a few catalogues, perhaps the largest single star we have ever found. And if you stepped outside right now and looked toward the shield, toward the exact patch of sky where all that fire is burning, you would see only ordinary darkness, and the familiar stars, and the still air of an ordinary night. The universe does not announce its extremes. It holds them, patiently. In rooms we have only barely learned how to open, so there the summit stands, wrapped in a number that stretches belief. And now, because I promised at the start of tonight that wherever the science stays open, I would say so plainly, we are going to do what the best tellings of this story do, and the lazy ones skip. We are going to examine every reason the famous figure might be wrong, and every reason it might, after all, be right. Take one slow breath here, and let it out longer than you took it in. The clear view from the top is next. Picture, for a moment, a lesser version of tonight's story, the kind that ends right here. One chapter early, title awarded, curtain drawn, sleep well, the biggest star ever discovered, 2,150 suns wide. Full stop. That would be an easy place to stop. It would also not be fair to you, since you have traveled the whole distance to get here. So in this chapter, we walk around the famous number and look at every place where it wobbles. By the end, I think you will find the wobble is not a disappointment. It is the most trustworthy part of the entire story. The first wobble you already know by heart, because it has followed us up every rung of the ladder. Distance, the star's celebrated size, assumes it truly sits alongside the Stephenson 2 cluster, 19 or 20,000 light-years away. The star itself is too distant and too deeply veiled for the parallax trick to settle the matter on its own. Even Gaia, the same great surveyor that redrew UY Scuti's story a chapter ago, reaches the edge of its powers out here. So the distance is inherited from the surrounding cluster, and that inheritance depends on the star belonging to the family in the first place. Which brings us to the second wobble. Does it belong? Here, the evidence points in two directions at once, and the fairest telling keeps both in view. On one hand, some measurements of the star's motion through space have not matched its 24 giant siblings as cleanly as astronomers would like, and it sits somewhat apart from the dense knot at the cluster's core. Findings along these lines led some researchers to suggest it might be an unrelated red supergiant, sitting closer to us or farther away, lying along a similar line of sight by coincidence. On the other hand, later work measuring the star's velocity directly from its spectrum has supported membership after all, finding it broadly consistent with the rest of the family. So the honest record is neither a rejection nor a confirmation. It is a history of conflicting clues, still being sorted through. If the star sits closer than the cluster, the arithmetic shrinks it considerably, the way it once shrank Scuti. If it sits with the family, the enormous estimate stands on firmer ground. The third wobble is the veil itself. All that dust between us and the shield does not simply dim the star's light evenly, it reddens and distorts it in complicated ways. And astronomers must model how much light was lost along the journey in order to reconstruct the star's true brightness. For a star buried this deeply, that correction is large, and every uncertainty folded into it flows straight through to the final size. The temperature carries its own doubt too, because pinning down the surface warmth of something this cool, this distant, and this thoroughly wrapped in its own shed material is delicate work. Even the star's identity has caused small tangles in the literature, with the same object occasionally appearing under different labels in different papers. A reminder that at this distance, keeping the bookkeeping straight is its own challenge. Depending on the distance adopted, the dust correction applied, and the temperature assumed, published and derived figures for this star's size span a wide range, running from roughly the size class of VY Canis Majoris all the way up to the record-breaking number. The famous figure is one of the largest well-known estimates in circulation. It was never presented, by the people who calculated it, as a settled fact. And there is a fourth wobble, the deepest and most interesting of all. Theory itself raises an eyebrow here. Stars. According to the working models astronomers rely on, should have an approximate outer boundary to how large and how cool they can become. A region on the great map of all possible stars where stable configurations run out. We will spend a whole chapter on that boundary soon. For now, what matters is this. Under the coolest published temperatures and the largest published sizes, Stephenson 218 would sit uncomfortably close to that boundary, or possibly past it. That does not automatically mean the measurement is wrong. Sometimes, the universe uses extreme objects to teach us that our models were built too timidly. But when an estimate lands at the very edge of what theory expects, careful scientists treat that as a flag worth investigating, a reason to measure again rather than celebrate. Either the star is somewhat smaller than the famous number suggests, or our understanding of giant stars needs some honest stretching. Both possibilities are exciting. Neither is resolved. So, let me say plainly, gathered in one place, what all of this adds up to, because you have earned the clearest sentence I can offer. Stephenson 218 is one of the largest known stars, and by the most widely repeated estimate, it stands among the largest radius estimates ever seriously proposed for any star. But that estimate was built from an inherited distance, a modelled brightness, and an uncertain temperature. And the star's family membership is still being debated, with evidence on both sides. Astronomers, therefore, tend to describe it as perhaps the largest known star, or among the largest candidates, rather than declaring an outright champion. The title of tonight's journey holds exactly as far as the best current science can carry it, and not one step farther. And here is why all of this should feel like a gift rather than a letdown. Think about what the Asterisk is. It is a group of human beings, scattered across observatories and decades, refusing to claim more certainty than their instruments can deliver, about an object 20,000 light-years away, that none of them will ever touch. They could have rounded up. Plenty of headlines and videos over the years did. But in the papers themselves, In the deliberate language of estimate and assumption and candidate, they kept faith with the evidence. Every giant of our evening was handled the same way. Betelgeuse's fuzziness, openly admitted. VY's debate, published from both sides. UY Scuti's famous figure surrendered when better data arrived. And that new data questioned in its turn. The asterisk is not a crack running through the story. The asterisk is the story. It is the sound of a species measuring at the very edge of what can be measured, and telling the truth about where that edge sits. Notice, one final time, the pattern underneath everything we have covered, through every revision and every debate. The stars themselves never changed. Stephenson 218 is exactly as large tonight as it was before Charles Stephenson noticed its neighborhood. Exactly as large as it will be when some future instrument settles the matter for good. The uncertainty lives entirely on our side of those 20,000 light years. Out there, in the star's own existence, there is no contest running, and no asterisk attached to anything, just a very old star, very far away, gradually letting go of itself in the dark. Some future night, a sharper measurement will arrive. Perhaps it will confirm the famous figure. Perhaps it will pass the title to a star nobody has heard of yet. Sitting right now in someone's forgotten catalogue, the way this one once sat in Stephenson's. Either way, you now know something most people never learn about the biggest star we have found. You know how we know it, how sure we are, and where the honest edges of our knowledge lie. That is a rarer, more durable kind of knowledge than any record, and it rests easier on the mind. Now, set the asterisk down. It has done its work, and it does not need to be carried any farther, because next, we stop measuring this giant from the outside, and we do the one thing no instrument can. We visit, safely, in imagination only. We drift down into the thin red mist of Stephenson 218 itself, to discover what it might feel like inside a star lighter than the air in your room. Everything we have done so far tonight, we have done from a distance. We have measured, compared, calculated, and doubted, always from the far end of a beam of light that took thousands of years to arrive. But there is one thing measurement can never give you, and that is the feeling of a place. So now we do the one thing no spacecraft will ever manage. We visit Stephenson 218, in imagination only, which happens to be the one vehicle that travels faster than light and never runs out of fuel. Let me be clear, in keeping with the spirit of tonight, about what this chapter is. No human being has ever been to any star. What follows is a thought experiment, a guided dream built from the real, published physics of red supergiants and hypergiants, the same measurements and models we have spent all evening learning to trust and to question. Where the science can speak, I will let it speak. Where imagination has to carry us, I will say so. And since this is only a dream, we grant ourselves the one impossible gift every dream is allowed. Nothing here can harm you. The heat cannot touch you. We are only visiting, so close your eyes a little deeper and come with me. We begin far away, where the star is still a deep red point in the blackness, and we drift toward it. The first strange thing you notice is how long the approach takes, and how little seems to change along the way. With an ordinary star, there would come a moment of arrival, a surface swelling up to meet you. Here, no such moment comes. The The star simply grows and grows until it is no longer a thing in front of you, but a direction. Down has become red. Half of everything that exists, from wherever you float, is now the dim, warm glow of one star, stretching past the edges of your vision on every side, so wide that your eyes cannot find its curve. You are still millions of miles from anything you could call a surface, and already the star has stopped being an object and become a landscape, a sky of its own making. Now we descend, and here is where the physics turns stranger and gentler than anything you might have guessed. You keep waiting for the wall, the clean boundary where space ends and star begins. It never comes. Remember what we learnt earlier, that a star like this has no crisp edge, that its outer layers thin outward gradually, like fog that never quite decides where it ends. Astronomers stating the radius of such a star are, in the most literal sense, drawing a line inside a cloud. And now you are floating inside the reason why. At some point during your slow descent, you realize it has already happened. You are in the star. There was no threshold. The blackness of space gave way, so gradually that you could never say when, to a faint, warm, reddish haze in every direction. You did not land on Stephenson 218. You dissolved into it, the way an airplane dissolves into a bank of cloud. And here is the fact this chapter is named for, one of the most delicious in stellar astronomy, told with the care it deserves. Under the famous radius estimate and the modest mass astronomers generally assign to a star like this, the gas around you out here, in this vast outer envelope, would be thinner than air, not slightly thinner, vastly thinner, closer to what an engineer on Earth would call a laboratory vacuum. This holds not only for the outermost wisps, but, under those same assumptions, for much of the star's overall average density as well, because a fairly modest amount of matter has been stretched across a volume that could swallow billions of suns. Deep down, near the hidden core, matter is packed, dense, and furious, hotter and heavier than anything in our solar system. But the immense outer body, the very part that makes this star so wide, is barely there in any ordinary sense. If you scooped up a jar of the star from where you are floating and carried it home, it would register on a scale as very nearly empty. You are drifting, in this dream, through a fire thinner than your own breath. What would you see? Models and observations of real red supergiants let us paint this with some confidence. Not flames, nothing like the roaring surface of the sun you might have seen in a documentary. Instead, a soft, deep, ember-colored glow, coming from everywhere and nowhere, brighter somewhere below you, dimmer somewhere above, like being suspended inside a sunset that never finds a horizon to set behind. The light feels calm and diffuse, the way light feels inside a lampshade. To your dreaming senses, the thin gas would seem almost perfectly still, though the star itself is far from still. Real currents move through it. Real shocks ripple outward from deep in the interior. A steady wind of escaping gas is forever leaving for open space, carrying small pieces of the star away, one breath at a time. It is simply that all of this happens at scales and speeds so vast that human senses, dropped into the middle of it, would read the whole thing as calm. The way a stormy ocean can look motionless from a high enough window, if you could watch on timescales far longer than any human patience allows. You would see the churning for yourself. Observations of stars like Antares and Betelgeuse indicate that their surfaces heave with enormous, slow convection currents, whole regions of rising and sinking gas so large that a single one can span a substantial fraction of the entire star, wide enough, in some cases, to swallow the orbits of the innermost planets. In our dream, we can speed time up and watch the red haze brighten and dim in slow, rolling waves as these vast continents of warmth drift past, each wave taking months or years of real time. It is weather of a kind, on a scale our sky has never known, moving with the unhurried rhythm of something that has never had a reason to rush. There is one more thing to feel out here, perhaps the gentlest of all: gravity. You might expect the mightiest star of the night to grip you mightily, but the pull at any spot depends not only on total mass, but on how far you are from the center. And you are floating almost unimaginably far from this star's core, out here in the thin red mist, by the models astronomers build for stars like this. The pull would be feeble, considerably weaker than the ordinary gravity holding you into your bed right now. This is precisely why these giants shed themselves so easily, why Canis Majoris throws off entire Jupiters of material in a single convulsion, why everything of this size is steadily letting go of itself. The star can barely hold on to its own outermost edges. In the most literal physical sense, you are more firmly held, resting in your bed tonight, than the material drifting through this star's outer atmosphere is held by the star itself. Let that thought settle as we begin to rise, up through the haze, watching the red, thin, back into blackness, so gradually that once again there is no moment you could point to as leaving somewhere far behind you, deep below the mist. A hidden core is still burning through its final reserves, and the long letting go continues exactly as it has for a very long time. Whether or not anyone ever dreams their way through it again, we surface back into open space, and the star shrinks behind us into a deep red lamp glowing in the dark. The visit is over, but there is one more room hidden inside this same dream. Stranger still, because there is a version of this thought experiment even more unsettling than traveling out there, and that is bringing the star here. We lift our own familiar sun out of the center of everything we know, set the giant down in its place, and watch from a safe and entirely dreaming distance what becomes of the neighborhood we grew up inside. Every comparison of our evening has pointed in one direction, outward, away from home, toward the shield. Now, for one chapter, we reverse it. We bring the giant home. Astronomers use this exact thought experiment constantly, because it is the only real way a human mind can grasp sizes like this. And we have already glimpsed its headline. Under the famous estimate, Stephenson 218 in our Sun's place would reach approximately as far as Saturn's orbit. But a headline is not a journey. So, let us take the journey properly, planet by planet, and carry one small lantern of caution the whole way. Everything in this chapter follows from the 2150 figure, the boldest and most widely repeated of the published estimates. If the true size turns out smaller, as it honestly may, the edge of the fire simply pulls inward to match. We are building this dream on the largest number available, and we will treat it that way. Begin at the center, The sun lifts out of the solar system like a marble lifted from a bowl, and in its place we set the giant down. And immediately, notice the first absurdity of the exercise. There is nowhere to set it. The star does not fit inside the sun's old spot. It does not fit inside the entire inner solar system. Placing it here is less like swapping one lamp for a bigger one, and more like pouring an ocean into a teacup saucer. So instead, we center it where the sun once was. Let its thin red body spread outward to wherever it naturally reaches, and then walk the old neighborhood to see what remains. Mercury disappears first. The little scorched world vanishing so deep inside the star's envelope that its entire orbit lies buried. Venus follows. Then Earth. Pause here, because this is home, the place where you are lying right now. The bed, the room, the roof, the town around it. The whole blue world, with its oceans and its history and everyone you have ever known, would drift deep inside the body of the star, wrapped in the same thin red haze we floated through in the last chapter, not burned on any surface. Remember, because there is no surface, only enveloped, absorbed into the ember-colored mist. Mars joins us next. The asteroid belt, every tumbling rock of it, joins too. Jupiter, the king of our planets, 300 Earths of mass, the world that has shepherded comets and shielded the inner solar system for billions of years, is swallowed along with its entire crowd of moons, well over 90 of them, known at last count. At these scales, even mighty Jupiter goes quietly, a pebble slipping into fog, and the red continues outward, past Jupiter, across the wide gap where no major planet lives, thinning as it goes, until somewhere right around 10 astronomical units from the center, it fades into open space. 10 astronomical units sits almost exactly at Saturn's average distance from the Sun. So, under the famous estimate, the ringed planet does not get to watch safely from a distance. Saturn skims the outermost edge of the star, grazing the last of its thin mist, perhaps just inside it, perhaps just outside. Depending on which version of the estimate you trust, and where Saturn happens to be along its slightly oval path, it is worth remembering that the quoted radius marks a conventional boundary, the layer where the star's light is considered to originate, not the literal final atom of its atmosphere, which likely drifts thinner still for some distance beyond. Picture the scene softly. The ringed planet, rings and all, sailing endlessly through the last faint breath of a dying star. Breathe out slowly here, and let the picture widen. The first clear survivors sit farther out, stunned, in imagination only, on a moon of Uranus, nearly twice Saturn's distance from the center of everything. On our real sky charts, the sun seen from out there is a brilliant, shrunken point, more a lamp than a presence. But in our dream, standing on that icy moon, there is no ordinary sky left. The star fills it. From that distance, the giant would span something close to 60 degrees of heaven, a deep red ceiling stretching well over a third of the way from one horizon to the other, dim enough in its cool enormousness that you could gaze straight into it, and even from Pluto, 4 times farther out than Saturn, where our actual sun becomes just one unusually bright star among countless others. The giant would still hang overhead as a glowing disk, something like 60 times wider than the full moon looks from Earth, dominating the frozen plains of the loneliest little world we know. There is one more comparison left, and it is my favorite of the evening, because it is not about space at all. It is about time. Think about an ordinary sunset. On Earth, the sun takes about 2 minutes to sink fully below the horizon. That brief golden window every photographer chases. The sun is small in our sky, and our world turns quickly past it. But size changes time in ways that feel almost unfair. The wider an object is, the longer any world takes to rotate past it. If a star of this scale were setting, watched from some safely distant world, turning at roughly Earth's pace, its trailing edge would still be sliding below the horizon many hours after its leading edge had touched down. A single sunset stretching across most of a night. Depending on how far away that world sits and how quickly it spins, you could fall asleep watching such a sunset begin, sleep through the whole night, and wake before it had finished. Somewhere out in this universe, around giants like this one, if any world sits at the right distance to watch. Evenings really might stretch that long. Now, before we step out of the dream, one steady breath of plain reality. None of this will ever happen. Stephenson 218 is not coming here. It sits 20,000 light years away, bound to its own distant neighborhood. And the gulfs between stars are so vast that stars essentially never collide or trade places. Our own sun, as we learned earlier, will one day swell into a red giant of its own, on a schedule roughly 5 billion years long. And even at its largest, it will never approach these dimensions. It is not massive enough to become anything like this. The dream was only a ruler, laid across the old neighborhood, so that a resting mind could feel what the famous estimate claims. The measuring is finished now. You are allowed to set the ruler down, and as the dream dissolves, and the giant lifts away, and our own small, steady sun settles back into its rightful place, warming Mercury again, lighting Saturn's rings from nearly 1 billion miles away, holding every world where it has always held them. You may notice a new feeling toward it. After a night among the giants, the sun feels different. Small, yes, we knew that from the first chapter, but also steady, compact, quietly competent, a star that holds itself together, that keeps its own edges, that will rise on schedule tomorrow over a neighborhood it has never once let drop. Somewhere across the last few chapters, an assumption may have settled into the room without your noticing, and now is the moment to lift it away. All evening, we have ranked stars by their width, and it would be natural to assume the biggest stars must also be the mightiest, the heaviest, the most powerful, the true kings of the sky. They are not. And the reason is one of the most satisfying corrections in astronomy. The kind of realization that makes the whole sky make more sense once you hold it properly. Here is the distinction, offered as one image. Think of a great old oak tree, and think of a hot air balloon floating beside it. The balloon is far bigger by any visual measure. It could swallow the oak whole with room to spare. But the oak is far heavier, denser, more substantial in every way that would matter on a scale. Size and weight are two different titles, and in the kingdom of stars, they are almost never held by the same star. Stephenson 218 is the balloon, for all its staggering width. Remember what we learned while floating inside it. Its outer layers are thinner than air. Matter, stretched across a volume that could swallow billions of suns. Its actual mass, the amount of star packed into the star, is estimated at only a few tens of times the mass of our Sun. Substantial, certainly, but not remotely exceptional among stars. This giant size is inflation, not substance. It is a moderately heavy star having an extraordinarily large final act. So where do the true heavyweights live? For that answer, we leave our galaxy entirely, hanging low in the southern sky, visible only from Earth's southern half. There is a soft, glowing smudge astronomers call the Large Magellanic Cloud. It is not a cloud at all. It is an entire companion galaxy, a smaller neighbor of our Milky Way, roughly 160,000 light-years away, slowly circling us the way moons circle their planets. Tucked inside, it sits one of the most spectacular objects in the known sky, a vast nursery of glowing gas called the Tarantula Nebula, the most furious star-forming region in our entire galactic neighborhood. Astronomers have noted that if the tarantula sat where our familiar Orion Nebula sits, it would be so large and bright that it would cast visible shadows on the ground at night. And in the heart of that nursery, packed into a dense young cluster called R136, lives the true heavyweight champion of tonight's journey. Its name, in the plain style we have grown used to, is R136A1. In 2010, a team of astronomers, led by Paul Crowther of the University of Sheffield, published a study of the brightest stars in that cluster, and the numbers startled even the specialists. R136. R1 appeared to hold well over 200 times the mass of our Sun, and estimates, published since, have generally settled somewhere between roughly 150 and 200 solar masses as the measurements were refined. Before that study, many astronomers believed stars simply could not form much heavier than about 150 suns. This one star forced the textbooks open again. A word about what kind of star it is, because the label matters. R136. A 1 is not a swollen giant of any color. Despite how it is sometimes casually described, it is classified as a Wolf-Rayet star. Of a hydrogen-rich type astronomers label WN5 #. Wolf-Rayet stars rank among the most extreme objects known, so hot and so furiously luminous that they drive ferocious winds off their own surfaces, blowing themselves thin from the outside in, even while burning fiercely within. This star is young, blisteringly hot, and very much in the prime of its life. The exact opposite in almost every respect of our dying red balloons. Now feel the contrast, because this is the heart of the chapter. R136. A1 carries several times more mass than Stephenson 218. It is, by that measure, considerably more star, and yet its radius comes to only around 30 or 40 times that of our Sun. Our evening's ladder would barely notice it. Under the famous estimate, the shrouded giant in the shield is roughly 50 or 60 times wider than this heavyweight champion. You could pour something on the order of 100,000 copies of the heavyweight into the volume of the size champion and still have room left over. The mightiest star known to science would vanish inside the biggest one like a coin dropped into a lake. But do not let its compactness fool you. That small blue furnace is ferocious beyond almost anything else we have met tonight. Its surface burns at tens of thousands of degrees. many times hotter than our Sun, and its total light output is staggering. Estimated at several million times the Sun's luminosity, million, Stephenson, 218, for all its impossible acreage, shines with a few 100,000 suns worth of light by comparison. The compact heavyweight outshines the sprawling giant many times over. From a body a tiny fraction of the size, it is the difference between a vast field of warm embers and one narrow, cutting torch. Both are fire. Only one is fierce, and that fierceness comes with a price, which brings us to the strangest law of stellar life. One we have been circling all evening without naming. The heavier a star is, the shorter it lives. It sounds backward. More fuel should mean a longer burn, the way a bigger tank means a longer drive. But a star's weight is also its crushing pressure. All that extra mass presses down on the core, and the core, to hold the star up, must burn catastrophically faster. The resulting numbers are almost unbelievable. Our modest Sun will live for roughly 10 billion years. A star of 10 solar masses lives for only tens of millions, and a monster like R136A1 is expected to exhaust itself in just a few million years. A span so short on cosmic scales that it deserves its own comparison. The dinosaurs walked the Earth for well over 100 million years. A star like this could be born, blaze, and die dozens of times over, inside the span of the dinosaurs alone. The greatest stars the universe knows how to build are candles burned at every end at once. Smallness, it turns out, is the secret of endurance. Our quiet little Sun will outlive every giant we have met tonight, and it will not be close. Before we leave the heavyweights, one more story, because our own galaxy holds a monster of this general kind too, and its history includes one of the most dramatic events ever watched unfold in Earth's night sky. In the southern constellation Carina sits a star system called Eta Carinae, whose primary star is estimated at perhaps 90 or more solar masses. In the 1840s, observers around the world watched Eta Carinae do something almost without precedent. It erupted. Over several months, this distant star brightened until, in 1843, it became one of the brightest stars in Earth's sky, briefly outshining nearly everything else, despite sitting some 7,000 or so light years away. Then, slowly, it faded back into obscurity. Astronomers call it the Great Eruption, and the star survived it, which is why it is sometimes described as a supernova imposter, an explosion violent enough to look like the real thing without destroying its star. The eruption hurled an estimated 10 or more suns worth of material into space, and that material is still out there, photographed by the Hubble Space Telescope as two vast glowing lobes shaped like an hourglass of fire, still expanding from an outburst first witnessed when the telegraph was brand new technology. The heaviest stars do not shed themselves gently, the way our patient red giants exhale. They convulse. Rest here for a breath, because the kingdom is now complete, and you have seen both thrones, the title of size, held provisionally by a cool red balloon of a star tucked into the shield, thin as breath, vast as planetary orbits, and the title of mass, held by a furious, compact furnace in a neighboring galaxy, blinding in its brightness and doomed to burn out in a cosmic instant. The universe does not allow any single star to have everything at once. The biggest are never the heaviest. The heaviest are never the biggest. And the brightest never last very long at all. All night, we have been climbing, and every climb quietly assumes the ladder keeps going forever. But you may have noticed something. The largest known size estimates hover around 2,000 solar radii, not 2 million. The heaviest known stars weigh in around a couple hundred suns, not a couple billion. The universe elsewhere contains galaxies holding 1 trillion stars apiece, and structures spanning hundreds of millions of light years. It clearly does not think small as a general rule. So why do the stars stop where they stop? Why is there a biggest star at all, rather than an endless ladder stretching upward forever? The answer is that the universe draws real lines, not fences of wood and wire, but boundaries written into the way matter and light behave together. In this chapter, we meet the two great ones, along with the two scientists who found them. This is the deepest science of our evening, and I promise it still fits into pictures a resting mind can hold. The first line belongs to light itself, and it was explored by one of the great figures of 20th century astronomy, a British scientist named Arthur Eddington. Eddington was among the first people to understand what stars actually are, working out in the 1920s how they hold themselves up, and correctly suggesting, long before anyone could prove it, that they shine by fusing atoms in their cores. Woven through his equations was a startling idea. Light pushes, we never feel it, because our lamps are far too feeble. But light carries real momentum, and as it flows outward through matter, it shoves that matter along with it. Sunlight, at this moment, is pressing ever so slightly on the roof over your head. Engineers have even flown experimental spacecraft called solar sails that travel on nothing but that push. Now, scale the effect up. Inside a star, the outward flood of light constantly pushes against the star's own body, resisting gravity's inward pull. In our sun, gravity wins comfortably, and the push of light is a minor detail. But the heavier and brighter a star becomes, the harder its own light shoves outward. Eddington saw where that trend leads. There exists a brightness for any given mass at which the outward push of light rivals the inward pull of gravity itself. Approach that point, and the star can no longer hold itself calmly together. Its own radiance begins stripping its outer layers away, like a fire burning so fiercely that it scatters its own fuel. Astronomers call that threshold the Eddington limit, and the real universe treats it less like a brick wall and more like a firm guiding principle that bends with the details. The exact ceiling shifts depending on what the star is made of and how its gas behaves. And extreme stars can hover unsteadily near it for a while without flying apart. But the principle organizes nearly everything we know about the heavyweights. It is why R136 A1 drives such ferocious winds off its surface, forever blowing itself thin. It is why Eta Carinae convulsed so violently in the 1840s, hurling 10 suns of itself into the dark. Those stars live pressed against the outward push of their own light. A star cannot be arbitrarily heavy and calm at the same time, because past a certain point, it would shine so brightly that it would begin unmaking itself through its own shining. Sit with that for a moment, because it may be the most beautiful rule of the evening. Among the things that keep the universe's fires in check is the sheer brilliance of the fires themselves. The second line belongs to the giants, our red balloons, and it was mapped in the 1960s by a Japanese astrophysicist named Chushiro Hayashi. Hayashi studied the internal structure of cool stars, stars whose bloated outer layers churn from top to bottom the way water churns in a boiling pot. His mathematics revealed a boundary of a different kind. On the great chart astronomers use to plot every known star by temperature and brightness, there is a region toward the coolest side where the equations stop offering stable answers. A star pushed toward that region, swelling and cooling as it goes, eventually reaches a place beyond which no steady configuration of its gas can exist. It cannot settle there. The chart, in effect, has a far edge, and cool giant stars lie crowded along it, unable to drift meaningfully further. Astronomers call that edge the Hayashi limit, and like Eddington's ceiling, it is an idealized boundary whose exact position depends on a star's mass and composition. It speaks most directly to cool, fully convective stars like the giants we have met tonight, rather than describing every kind of star equally. Hot, compact stars like our heavyweight champion answer to different limits. But the message is plain. There is only so large and so cool a star of this kind can become, and still hold together as a star at all. Now listen to how the whole evening clicks into place around this idea. What is the estimated surface temperature of Stephenson 218? Somewhere around 3,200 kelvins, right in the general neighborhood of that far edge. Under the coolest published temperatures and the largest published sizes, the star in the shield would sit essentially on that boundary, or arguably past it. That is exactly why, back in our chapter on the Asterisk, careful astronomers treated the famous radius as a flag worth investigating rather than a settled verdict. For a star claiming to live at the very edge of what is physically possible is either a measurement stretched by distance and dust, or a discovery pressing on the theory itself. Both of tonight's champions, it turns out, dwell against their own boundaries. The heavyweight burns hard against the ceiling of light, forever shedding. The giant drifts along the far edge of coolness, as swollen as the mathematics currently appears to allow for a star of its kind. There is one more boundary worth knowing, at the opposite end of the scale, and it completes the picture with a pleasing symmetry. Stars have a minimum too. A ball of gas, weighing below roughly 8% of our sun's mass, can never squeeze its core hot enough to ignite sustained hydrogen fusion. It becomes instead what astronomers call a brown dwarf, a would-be star that glows dimly with leftover warmth and slowly cools forever, a lantern that never quite lit. So every star that has ever truly shone, every point of light in every night sky over every sleeper in human history, has lived somewhere inside a bounded landscape, closed at the bottom by ignition, and shaped at its outer reaches by the push of light and the far edge of coolness we just explored. Let your hands rest open for a moment, and consider what the limits have given in return. We spend our lives uneasy about limits, deadlines, ceilings, boundaries, edges. The word itself carries a small sting, but because stars cannot be infinitely heavy, they do not all flash brilliantly and vanish, because they cannot swell without end. They hold together long enough to warm entire families of planets, because there is a floor and a ceiling. There is a wide, comfortable middle, and in that middle live the steady, long-burning stars, the ones that last billions of years, the ones capable of holding worlds in stable orbits while life takes its time arising nearby. Our Sun is not remarkable because it presses against any boundary. It is remarkable because it sits so comfortably far from all of them, and now only one part of tonight's story remains untold. We have watched the giants swell and shed and press against every line the universe has drawn. We have not yet watched how it ends. Every red giant of tonight's journey, Betelgeuse and Antares, Vy and Uy, and the shrouded candidate in the shield, is walking toward the same final hour. The collapse and the light. The supernova itself. It sounds, on paper, like a chapter built from violence. It is actually, as you are about to hear, one of the most generous moments the universe has to offer. The moment the giants give everything away, including, quite literally, some of the ingredients of you. Every story we have told tonight has been walking, without any hurry, toward this chapter. Betelgeuse, breathing out its curtain of dust. Antares, simmering at the heart of the scorpion. Canis Majoris, standing in the wreckage of its own eruptions, and the shrouded giant in the shield, loosening its grip on itself. Year by year, every one of them is doing the same thing. Every one of them is getting ready. So before our journey closes, we are going to watch, safely and from the softest possible distance, how the life of a giant star comes to an end. I will tell you now, before we begin, how this chapter finishes. It finishes with you, not as a figure of speech, but as a plain statement of physical fact, supported by decades of careful astrophysics. Hold that promise, and come watch the last act with me. Return, in imagination, to the deep interior of a dying supergiant. All evening we have spoken of these stars burning through their final reserves, and now we can say precisely what that means. A star like this spends its long adulthood fusing hydrogen into helium, the way our Sun is doing right now. But once the hydrogen runs low and the core contracts and heats, something becomes possible that never was before. The helium ash itself begins to fuse, forging carbon, and once the helium runs low, the core contracts and heats again, and the carbon begins to fuse. So it continues, stage after stage, each new fuel scarcer, hotter, and faster burning than the one before. The star becomes layered like an onion, shells of different fires stacked around a core, reaching for heavier and heavier elements. Carbon, oxygen, neon, silicon, each stage shorter than the last. The hydrogen burning phase lasts millions of years. By the time the core is fusing silicon, the standard models tell us that final stage may burn for only about a single day, and then the star arrives at iron, and iron is where the universe closes the door. Here is the physics behind that closing. Every fusion stage before this point releases energy, and that energy is what holds the star up against its own gravity. But the nuclei near iron on the periodic table are among the most tightly bound in nature. Fusing them further does not release energy. It costs energy. The moment a massive star's core has turned to iron, the long bargain that defined its existence, fire pushing outward against gravity, pressing inward, is over. The furnace at the center has nothing left to burn, and gravity, which has waited without a moment of impatience for millions of years, finally wins the argument. What happens next unfolds faster than anything else we have described all evening, and I will keep the telling soft. The core collapses. In a fraction of a second, a ball of iron, roughly the size of a planet, crushes down into a sphere perhaps a dozen miles across. Matter squeezed to the density of an atomic nucleus. The infalling outer layers slam onto that newborn core, and a shockwave is born, racing outward through the star. And here modern science has added a wonderful, subtle detail to the old textbook picture. The shock, left on its own, usually is not enough. Careful simulations show it tends to stall partway out, hesitating inside the collapsing star, almost as if the explosion were briefly unsure of itself. What appears to revive it is the strangest rescue in physics. The collapsing core releases an almost inconceivable flood of ghostly particles called neutrinos. And although neutrinos famously interact with almost nothing, there are so staggeringly many of them, packed into such dense surroundings, that their combined heating, together with violent churning motions building behind the stalled shock, appears to breathe life back into it. The revived shock tears outward through the rest of the star, and the giant, at last, lets go of everything at once. From the outside, an observer would see a point of light bloom in the dark until, for a few weeks, that one dying star can outshine the combined light of its entire home galaxy. Astronomers call this a supernova. It ranks among the most powerful events the universe produces, and the giants of tonight's journey are generally expected to end this way. Assuming their current classifications and estimated masses are correct, humanity has watched this happen. In the year 1054, astronomers working in China recorded a new star blazing in the constellation we now call Taurus, bright enough for a time to be seen in broad daylight. It faded over the following months, exactly as they noted in their records. Nearly 1,000 years later, telescopes pointed at that patch of sky find the Crab Nebula, a vast tangle of glowing shreds still expanding from that long-ago explosion, with a small, furiously spinning stellar remnant at its center. And in 1987, a supernova bloomed in the large Magellanic Cloud, the same neighboring galaxy where our heavyweight champion lives, close enough for modern instruments to study in detail. Detectors on Earth even caught a burst of neutrinos arriving from the collapsing core itself, particles that had flown outward from the moment of a star's death and arrived after 160,000 years of uninterrupted travel. The last act is not a theory on a chalkboard. We have watched it happen, and taken its pulse as it did. What remains behind depends on the star. The collapsed core of many giants becomes what astronomers call a neutron star, and this may be the strangest object in our entire journey. Imagine the mass of one or two suns, everything we spent our first chapter learning to feel, compressed into a sphere about as wide as a small city. Matter so dense that a single teaspoon of it, by the standard comparisons astronomers use, would weigh something on the order of billions of tons. Some neutron stars spin many times every second, sweeping narrow beams of radio light across the sky like impossible lighthouses. And for the very heaviest giants, even that is not the end. The core collapses past every remaining form of resistance and becomes a black hole. a region where gravity has folded space closed around it. The brightest things the universe makes eventually become the darkest things it holds. There is a strange poetry in that, and the universe seems entirely at peace with it. But none of that is really why this chapter exists. Here is the reason. Ask the simplest question about the room around you. Where did the stuff of it come from? The iron holding together the frame of your bed, the calcium in your bones, the oxygen you are breathing at this moment, and the carbon in every cell of you that is resting. Listening, the universe began. Cosmologists tell us with real confidence, holding almost none of those ingredients. The Big Bang produced hydrogen, helium, and only the barest traces of anything heavier. Everything else had to be manufactured afterward. Somewhere, by something. That somewhere, overwhelmingly, is the stars. The great insight of 20th century astrophysics, worked out by scientists including Fred Hoyle and his colleagues Margaret Burbidge, Geoffrey Burbidge, and William Fowler in a landmark paper published in 1957, is that the ordinary elements of everyday life were forged inside stars, in the layered fires we just watched, and the full story, traced across the decades since, turns out to be richer than any single sentence could hold. So let me give it to you in 3 clear strokes. Massive stars, like the giants of tonight, forged much of the oxygen and similar elements, scattering them in their final explosions. Other kinds of stars contributed heavily elsewhere, with much carbon breathed out by modest sun-like stars late in their lives, and much iron delivered by the detonations of white dwarfs, the compact remnants of smaller stars, and some of the heaviest elements of all, including traces of the gold in the world around you, are now thought to come from collisions between neutron stars, remnants meeting in the dark long after their own endings. Different stars, different endings, one shared result. The ingredients of the world were made overhead and delivered downward, across billions of years. So, the promise made at the start of this chapter comes due. Every giant of tonight's journey is walking towards some version of the fate that helped build you. Somewhere in the deep past, stars very much like Betelgeuse, like Antares, like the shrouded candidate in the shield, along with countless others of every size, swelled and layered and let everything go, each in its own way, and some small share of what they gave is lying in your bed right now, breathing slowly, listening to a story about its own oldest ancestors, the supernova, and every other stellar ending alongside it, is not the tragedy at the end of a star's life. It is the inheritance. The giants do not merely die, they provide. Every title we have followed tonight was temporary, and by now you know that this is not a flaw in the story. It is the engine that drives it. Betelgeuse was the first giant with a face until larger faces were measured. Canis Majoris was called the largest known star until the numbers softened. Scuti held the internet's fame until Gaia looked closer, and Stephenson, 218, holds the celebrated estimate now, provisionally, with an asterisk we have examined in full light. So in this chapter, the second to last of our journey, we look forward and ask a question with a wonderful answer waiting behind it. Who is next? And how will we find them? The first thing worth saying is the strangest. The next recognized champion is likely already shining somewhere tonight. Red supergiants live and die within a few million years. But our instruments improve on a timescale of decades. So, whatever star eventually claims the title next is most likely one that is already burning. Its light already in flight toward Earth. Its entry, quite possibly, sitting this moment in someone's catalogue under a plane. Forgettable designation nobody has looked at twice. That is how it happened every time before. Scuti sat in the Bond survey for 150 years before anyone noticed. Stephenson, 2 waited decades between its first cataloguing and its discovery. The future of this story, if history is any guide, is probably already filed away somewhere, misjudged and waiting. So where will the better numbers come from? Let me introduce you, briefly, to the hunters at work while you rest, because each holds a different piece of the puzzle. The first you already know. Gaia, the European Space Agency's great surveyor, keeps refining its map of more than 1 billion stars with each new release of its data, sharpening distances that earlier astronomers could only estimate. And distance, as this whole evening has taught us, is the master key. Every improved parallax quietly resizes some star in the catalogues. Some giants will shrink in the ledger, the way Scuti did. Others, and this is the delicious part, will grow. Somewhere inside Gaia's enormous dataset, there may be stars whose distances were underestimated. Modest-looking entries that are actually farther away than believed, and therefore brighter, and therefore larger than anyone currently realizes. The next champion may be promoted rather than discovered. The second hunter is the James Webb Space Telescope, launched in December of 2021, the most powerful space telescope humanity has built. Webb matters to this story for one specific reason. It sees in infrared. Remember what unlocked Stephenson 2 in the first place. The largest stars hiding in the galaxy tend to lurk behind curtains of dust. In the crowded inner regions of the Milky Way, where visible light cannot travel far, and infrared slips through that curtain the way warmth slips through a closed window. The biggest stars we have not yet found are almost certainly not sitting in our clear, familiar sky. They are behind the smoke, in places only eyes like Webb's can reach. The third hunter is new, and belongs to this decade. High in the mountains of Chile, an observatory named for the American astronomer Vera Rubin has begun one of the most ambitious projects in the history of astronomy. A survey designed to photograph the whole visible southern sky again and again, every few nights, for 10 straight years, building what its scientists describe as a decade-long movie of the universe. Rubin's gift to our story is catching the restless ones. Red supergiants pulse, flicker, dim behind their own dust, and occasionally erupt without warning. A survey that watches everything repeatedly will naturally flag exactly the unstable, changeable stars that belong on any list of candidates. But let me be fair about the division of labor, because no single instrument does all of this alone. Rubin finds and flags the promising ones. Pinning a candidate down still takes an orchestra. Gaia for the distances. Radio telescopes for the motion of gas around a star. Interferometers descended from Michelson's steel beam for angular sizes. Spectrographs and infrared eyes for temperatures and dust. The next widely cited number, whenever it arrives, will be built the same patient way the current one was. by many careful hands, working in sequence. Let your shoulders settle a little heavier now, because there is comfort in what comes next. A moment of fairness about the future is worth including, because there is a version of this chapter that oversells it. And we are not writing that version. It is entirely possible that no star will ever be found meaningfully larger than the current candidate. Remember the far edge we explored 2 chapters ago. If the underlying models are broadly correct, stars cannot swell far beyond the scale we have already reached. And Stephenson, 2:18, or whatever star ends up confirmed near that scale, may already sit close to the practical ceiling of the universe's architecture. The great work ahead may not be about breaking the record at all. It may be about nailing it down, closing the asterisk, turning perhaps the largest into a settled answer at last. And honestly, after everything tonight has shown you, that would be the more satisfying ending. Records thrill for a moment. Certainty, in a field like this, is the rarer treasure. There is one more possibility, and it is the one I find loveliest to fall asleep on. The question may be settled by an ending. Every star on our ladder is living through its own final act. Betelgeuse, Antares, V. Oi, the shrouded giant in the shield. All of them are generally expected to end in collapse and explosion, assuming their current classifications are correct. On timescales stretching from thousands to hundreds of thousands of years, which means it is overwhelmingly likely to happen long after all of us, though not with absolute certainty, someday, and it could in principle be any day. One of the giants we visited tonight will finish. A point of light will bloom in Earth's sky, bright enough, perhaps to see in daylight, as the guest star of 1054 once was. And when that happens, astronomers all across this planet, some of them children right now, some not yet born, will turn every instrument humanity owns toward it and watch, in real time, everything this journey has described: the collapse, the light, the scattering of a giant's lifetime of forged elements into the dark, on their way to becoming something else. Somewhere in the far future, that debris will fold into new stars, new worlds, and, if the universe repeats its oldest habit, new sleepers, resting on some quiet evening yet to come, built in part from the very star we spent tonight measuring. So here we are, at the last chapter, resting at the quiet end of the longest ladder in the sky, and I want to spend it, if you will let me, not on any single star, but on one plain word, the word in the title of tonight's whole journey, biggest. We have used that word all evening as though it were simple, but you have watched, chapter by chapter, what it took to say it honestly about anything at all. It took 2 eyes and a finger held out at arm's length. It took the width of Earth's orbit pressed into service as a measuring stick. It took Bessel catching a shift the width of a hair seen from 200 feet away. After months of watching, it took Michelson and Pease on a cold December mountaintop, watching fine stripes of starlight fade. It took Herschel's Garnet and Lalande's Ledger, and a Bond survey holding 1/3 entries. It took Stephenson noticing one small smudge, and Davies clearing away the smoke around it, and Humphreys and colleagues assembling 3 uncertain ingredients into one widely repeated figure. reporting the assumptions and uncertainties alongside the result. The word biggest, it turns out, is not a fact you find lying around. It is a structure you build, generation after generation, out of care and honest attention, and it stands only as firmly as its most uncertain measurement allows. There is a second meaning underneath the first, one that only became visible near the summit of our climb. Nearly every star competing for this title is a star in its final act. That is not a coincidence. It is the rule. The swelling is the ending. In the kingdom of stars, biggest never means strongest, or brightest, or most enduring. It means furthest along. The word we chased all evening for its sense of wonder turns out, up close, to mean something nearer to oldest, or nearly finished, or letting go. The giant in the shield is not the mightiest thing we met tonight. Not by a wide margin. It is among the most generous. Standing in the last act of a long performance, whose finale scatters everything it ever made into the dark. For the benefit of others, it will never meet. Which brings me to the last measurement of the night. This one requires no telescope. All evening, we have measured in one direction, up and outward, from small toward large, Earth into Sun, Sun into Betelgeuse, Betelgeuse into the shrouded giant. 10 billion suns of volume, 20,000 years of traveling light. Climbing that ladder, it becomes easy for a resting mind to arrive at a conclusion the numbers never stated. That small must mean insignificant, that a world which vanishes into the mist of one star's outer layers, a bedroom that could be lost 1 billion times over inside a single fire, must not amount to much. I want to close by measuring in the opposite direction, because the same ladder looks completely different, climbed downward. Consider what exists inside your room right now, and nowhere else we have found tonight. On Stephenson 2:18, for all its impossible acreage, there is, as far as anyone can tell, no thought, no memory, nothing that has ever wondered about anything. The largest star we have seriously proposed has never known that it is large. It cannot know. It is magnificent, and unaware of its own magnificence. 10 billion suns of volume without a single question inside it. And here, resting on a speck far too small for that star to ever notice, is a mind that spent this evening holding the entire ladder in place. You crossed 20,000 light years tonight without moving from where you lie. You floated inside a star lighter than air. You watched a famous number being built, piece by piece, and came to understand which pieces might still shift beneath it. The universe built things of unimaginable size. And then, at least once, in at least one small corner of itself, it built something capable of measuring them. Nobody knows how rare that achievement is, but nothing we met tonight, in all those billions of suns worth of volume, suggested it is common. The people scattered through our story understood this. I think, somewhere in their bones, it is why they kept going, year after unglamorous year. Stephenson, cataloguing away in Ohio, Hayashi bent over his mathematics, Eddington working out the push of light, Humphreys and colleagues weighing a giant's brightness and publishing the caveats along with the number. None of them ever touched a star. All of them touched something rarer. The truth about stars, which is a different kind of contact, and in some sense a more intimate one. The stars do not know their own sizes. We know it for them. That is the strange, tender arrangement the universe seems to have settled into. And tonight, simply by listening to how it was done, you took your own small place inside it. So let the word biggest come to rest now. On your nightstand, beside the asterisk we set down hours ago, the biggest star we have found is, by the most widely repeated estimate, a red supergiant called Stephenson 218, roughly 2,150 suns across, if the celebrated figure holds. Shrouded behind the dust of the shield. Its title held provisionally. Its uncertainties known and kept honestly in view, currently letting itself go one breath at a time. That is the true answer, whole and unrounded. And you are now one of the comparatively few people on this planet who knows not merely the name of the thing, but the architecture of care underneath it. And the smallest thing in tonight's story, the warm, breathing, thinking speck at the bottom of the ladder, turns out to be the only part of it capable of holding the whole climb inside itself. From the first rung to the last, let your whole body settle now, one final time, into whatever is holding you. Nothing out there needs anything from you. The giant will go on burning without your attention. Gaia will keep refining. Webb will keep peering. Rubin will keep filming. All on schedules that ask nothing of your sleep. The stars have their boundaries. The famous estimate has its honest asterisk. The future has its patient instruments. And every piece of it will still be true. And still quietly working. When you wake tomorrow morning, you measured the universe tonight. Gently, from a single small room, the universe, in return, asks only that you rest. And that is where our journey ends for tonight. Let the numbers go now. The radii and the light years. The temperatures and the distances. They will keep themselves safely, the way they always have, somewhere behind the dust of the shield. That star is doing exactly what it was doing when our evening began, glowing deep red, shedding itself into the dark, unaware of its estimate, its asterisk. And you, some small part of its light will arrive, faint and unhurried, while you sleep. If this journey brought you a little wonder, or helped the weight of today loosen its grip, a like or a subscription helps these slow explorations find other people lying awake somewhere too. Nothing more is asked of you tonight. Let your breathing find its own pace now, and let your thoughts drift loose, easily, without alarm. Good night. Sleep deeply, beneath a sky that keeps its giants very far away, and keeps you exactly where you belong.